Yeah, okay. I think we can get started now.
Oops. Okay, let's go ahead and get started this morning. I'm Joe Klemp from the Mesoscale and Microscale Meteorology Laboratory. And on behalf of NCAR and our M-Cubed lab, I would like to welcome all of you to our annual WRF MPAS Users Workshop. It's pretty amazing that this will be the 23rd year we've convened the WRF Users Workshop, and for the last 5 years, it's been a joint workshop with MPAS users as well. Unfortunately, as you can see, this workshop is taking place in a virtual mode again. For those of you who were at the workshop last year, you know that we were also in virtual mode because of COVID at last year's workshop. And in that workshop, we expressed our strong hope and expectation that we would be in an in-person mode for this year. Unfortunately, that hasn't quite worked out. NCAR is in the process of opening up, but still hasn't quite gotten to the point where we can accommodate a large workshop like this one. But as we said last year, I'll say again this year, we certainly hope and expect that next year we will be able to convene the workshop in an in-person mode. We've certainly heard from many of you emphasizing the value of having the workshop be in person, where users and participants can have the opportunity for more informal and casual interactions with their colleagues and also model developers. One of the, I suppose, positive aspects of a virtual format is that we have a much larger contingent of registered participants. As you can see, we have almost 400 folks that are registered, which is about double what we would have in an in-person format. Over half of you are spread around in different countries, some 62 countries around the world, and over a third of the participants are students. With folks spread out all over the world, there isn't any good time frame that works for everybody. And so unfortunately for some of you, it may be the middle of the night and or other odd times during the day. But we're trying to compress our meetings into about a 3.5 hour time slot each morning here in Boulder, so it doesn't drag on too long for everybody. We're going to be having sessions today, tomorrow, and Thursday. We started yesterday with instructional sessions on a couple of topics, RAGEN and MPAS. This morning will be primarily dedicated to development updates, which is what we usually do on the first day of our workshop. And then Wednesday and Thursday will focus on model applications in a variety of areas. Each morning sessions, we will have a number of talks to start out with. Then we'll have a 15-minute mid-morning break, and then finish with the second half of the morning sessions. We're also leaving a short period at the end of the second morning session for questions and discussions. If there's questions that you wanted to ask a speaker and didn't have time to, you could fit them in there, or any other more general issues. So that will be the same format on Wednesday and Thursday. A couple of things to be emphasized here for participants and speakers. For the contributed talks, the speakers will have 15-minute time slots. And so we ask the speakers to please limit their presentations to 12 minutes to allow several minutes for discussion. When everyone connected, you were automatically muted, and we ask you to keep yourself muted unless you are asking a question. In order to contribute any comments or questions, we ask you to either use the chat or the raise hand function in the dashboard. And then following a presentation, the moderator will convey questions to the speakers following their presentations. If any of you are having trouble with your connections being too slow, or problems, sometimes turning your video camera off could be helpful in improving your connection. So with that, why don't we go ahead and get started? And I will turn the session over to Jordan Powers, who is the session chair for the first session. So, Jordan.
Thank you, Joe, and welcome to all the participants out there across the web. As Joe said, we've been doing this a long time, so it's a homecoming of sorts, even though it's virtual. So welcome, everyone. The first session is going to cover updates in component areas of the systems at WRF and MPAS, as well as new development directions that affect WRF and MPAS. As Joe mentioned, if you're a speaker, be mindful of your time and reserve the final few minutes for questions. If your time allotment is gone, then questions will be taken on your topic at the end of the session. Just to note, the first two talks in this morning's session will be 20 minutes and the other ones are 15 minutes. Okay, so to start us this year, we will hear from Dr. Jimy Dudhia of NCAR talking about the WRF model, an annual update for 2022. Jimy.
Thanks, Jordan. Yes, this is the usual first talk of the workshop. I'll give you an update of what we've been doing in the past year. So this is the history of the WRF releases. The first one was in 2000. The green are what I'll be talking about today. I'll also give a recap of what happened, what we released, what I talked about last year in version 4.3. But since then, we've had 3 bug fix releases, and then the major release 4.4, which was in April this year. So first will be the recap of the new features, bug fixes, and some verification tests of the version 4.4 release. This is just a reminder of what I talked about last year. Last year, we added the new E-Epsilon PBL scheme from Chunqi Zhang at NCEP. We added the Taiwan NTU microphysics scheme, the 3-moment version of the P3 microphysics scheme was new last year. Enhanced gravity wave drag from GSL and NOAA, Mike Toy's gravity wave drag option, and then the implicit explicit vertical advection from Lou Wicker, which speeds up the model and is used in the rapid refresh. Also, we added the solar eclipse capability in a few of the radiation schemes, extended the multi-layer urban models to the YSU PBL. We added local climate zones, which are an urban option for land model, the new urban categorization, which is much more detailed for land surface model. Green roofs and solar panels, no MP irrigation option, and the initial CTSM coupling capability. Let's see. And minor, dynamics option for vertical geopotential advection. Height level outputs were updated to include pressure. MAD-WRF is a WRF solar capability which initializes clouds, and clear sky 3D radiative efficiencies have been added for most schemes last year. Bug fixes since version 4.3. 4.3.1 was released in October 2021. In the initial release of the 3-moment P3 scheme, it wasn't working well, so this bug fix was important for anyone who wants to use that option. There was also some fixes to the solar panel option. Thomson's surface fluxes were fixed because there was the grid size dependency that we removed. And greenhouse table option, we added SSP scenarios, which is the new CMIP 6 scenarios, and other minor changes for 4.3.1 are detailed in the webpage. 4.3.2 was December 2021. We added time varying greenhouse gas option to the shortwave scheme, which wasn't there before in RTMG. That's a relatively minor effect because greenhouse gases have less effect apart from water vapor, which was already from the model in the shortwave. There's a slight CO2 effect. But in terms of time varying, it's not an important addition there. Test was introduced to stop certain combinations of PBL and LES schemes. People have had trouble when they put LES on the nests and PBL on the coarser domains with certain options like MYNN. There's also a workaround on our issues page. And some other minor details on the page. And 4.3.3 was released in January 2022, where we allow time series for certain options and other minor details on that webpage. So now for version 4.4, which was released in April, we've added accumulated physics tendency outputs. So you can output the tendency from each of the physics in accumulated form, which gives you more accurate budgets. The Thomson aerosol scheme includes black carbon. It's not interactive with the microphysics, but has a more complete radiation aerosol interaction with that option. iCloud 3 was updated. That's a cloud fraction option from Greg Thompson. All the P3 microphysics options have been updated. The RTMG radiation has a new cloud overlap option with a decorrelation length scale. NOMP has many new options. There's also a separate talk on that, so I won't go into that. Minor updates to the RUC LSM, MIN surface layer and Xinhuang PBL. The NMM dynamical core is no longer in the WRF code, so that was removed and has helped us clean up the code quite significantly. And the CMAC two-way coupling has been enhanced. There is now two-way coupling between WRF and the CMAC model, which is run offline from WRF, but can interact with WRF through the radiation. Again, there's a web page with more details if you want those. I'll go into the bigger changes now in version 4.4. Since in version 4.2, we made the CO2 year dependent via an empirical function in the RTMG long wave radiation. Since then, we've changed. We've also had since 2013 a compile time option with the -DCL WRF GHD to use year-dependent tables for all the major GHGs taken from IPCC scenarios such as RCP 8.5. Those span the years 1765 to 2500. So there's future scenarios there as well. And there's several tables with different future scenarios. And then that's been available for these radiation options listed. In version 4.4, we've made that the default, and it's now not compile time, it's just a switch in the model. And the default is GHG input 1. It uses these tables, including the new SSPs tables that I mentioned from the earlier releases. And if you still want the old method, you can switch using GHG input equals 0. So the difference is it's not a compile option, and it's now the default option to have these time varying greenhouse gases. So when you're using past or current or even future years, the table will tell the model what values to use for things like CO2 and methane especially. There are more IPCC scenarios available, as I mentioned, through these CAMTR files, so you're found in the run directory. The default is now the SSP2 4.5, which is a CMIP6 scenario for the future trends. But these are the ones we have listed at the bottom there. Another new thing in version 4.4 is the shallow water roughness length that has been based on the paper by Pedro Jimenez and myself in JMC in 2018. It's shallow water Z0 option. For shallow water depths less than 100 meters, there are shoaling effects, which is where waves appear rougher for the same wind speed in shallow water. So we wanted that, and that roughness effect affects the wind. So unless accounted for, this leads to a systematic overestimation of up to 10% of low-level wind speeds, as detected in comparisons in this paper with a year of North Sea tower data at 30-meter water depth. The option modifies the roughness length empirically fitted to the data as a function of wind speed U star. The depth dependence between 10 and 100 meters follows Taylor and Yelland. And we can now also use the real bathymetry, which is available through WPS. So you can have a map of the depth, or you can choose a fixed shallow water depth by specifying a number in this nameless option. A little more on this, the drag coefficient, this is wind speed on the axis and various parameters. So drag coefficient CD in the new scheme is this dark blue or black color. It increases more realistically compared to the observed drag coefficients, which are these, this observed ones are at 18-meter depth, but it's following those for the model as well. These are two older formulations. The Charnock is the default, which doesn't have the drag increasing so much for these higher wind speeds. So this is the effect of shallow water. The wind speed does have higher drag. Also, it can be seen in the friction velocity. You can see they converge quite a lot at low winds, but it's at 10 meters per second or higher winds that you start to see more significant effects. The roughness length also, this is a log scale here. Our new formulation is very linear compared to Charnock, and the other one we're comparing here is Edson. Again, even though there's a wide variation of roughness length at low wind speeds, it has very little effect on the U star. And I'll show the verification here. So the old formulation is this this reddish color. Well, this is a percentile plot. So it's a distribution of WRF versus the observations for different wind speeds. So it's there's a point, actually there's 100 points along here, which we just joined with a line. Each one is a percentile. So it shows the amount, the percentage, how the percentage at each wind speed compares between the model and the observation. So at the top percentile, 100 percentile, the model wind speed in the old formulation was high versus the observed one by maybe 1 or 2 meters a second. And you can see that the model tended to have too many, the high end of the distribution had a longer tail effectively. The 25th and 75th percentiles are marked in these dashed lines. So these are rarer winds outside that 75th percentile, but 100th percentile is at 20 meters a second. So the new scheme has brought it down to the blue line. The spread is related to different PBL schemes, and those PBL schemes didn't help. But changing now to a new formulation was tuned to bring it down to the blue line, and it's more on the one-to-one line now with the wind distribution. So we've removed that high bias at high winds. Next new feature is the stochastic ensemble perturbations. Pedro is talking a little about that later, and then Joo-Hae Kim has another talk later in the workshop on that. It's a WRF solar application, and the perturbations are added to selected physics suites, the deselected physics suite of WRF solar, which is the FARMS radiation. FARMS is a surface radiation that interacts directly with the model time step and clouds. NYN PBL, thing, shallow cumulus, Thompson microphysics and cloud fraction, and the NOAA LSM. the variables are selected for perturbations. The variables selected for the perturbation are chosen for solar energy forecast sensitivity, but they're customizable, so you can change them in the table. There's a table you can change the perturbation size. You can also change the magnitude, the standard deviation, and the space and time scales of the perturbations. It's built on the existing stochastic functions we had for SCABs in WRF. Now I'll quickly go on to tests and verification. We did tests for a lot of the new options on this grid, 15-kilometer grid. We did spring and winter cases, multiple cases in each on that grid in each season. So the results I'll show will be multiple cases per month, maybe about 10 to 15 cases per month. These are the tests we did. The default settings are in standard version 4.3 and 4.4. We also tested to make sure 4.4 didn't differ too much from 4.3. Then there's these tests that I'll list here, but I won't go much into due to time. I'll just show some results. This is the surface verification as a function of forecast time, 0 to 48 hours, 0Z. There are 0Z initializations, which are evening time. So the night time is early in the forecast, 6 and 12 are nighttime, 18 and 24 daytime. The thing that stands out here is the NOAA MP, which is different from the default is NOAA. So NOAA MP has less wind bias. You notice here. I'll come back to that later. The other biases are less obvious. The NOAA MP tends to have higher moisture during the nighttime as well. But as you see, most of the other tests we did comparing new features haven't dramatically altered our verification. And this is the profile verification for winds, temperature, and moisture again. The bias is on the top line. NOAA MP again, slightly warmer in the boundary layer, as you see here, especially in the daytime, 24-hour, 48-hour forecast. This is the same thing for the winter. The colors have changed, but NOAA MP now still has less wind bias and slightly more moisture. They're all around not too far from 0, so it's just a difference from the default, but not necessarily better or worse. And it has probably less mean moisture bias, NOAA MP, than the others, which tend to have a drying drift over the forecast time. And this is the profile verification again, showing the slightly warm bias in NOAA MP in the daytime. It's not really a bias because the 0 is here. So it's actually doing a little better than the default in terms of the temperature. I'll compare NOAA MP and NOAA more directly here in these just 2 lines. The NOAA is, so it's basically the standard setup in the standard physics involved, the only difference now being NOAA MP versus NOAA. So we see a lower wind bias again in NOAA, slightly more peaked daytime, 2-meter temperature, more moisture, both in the spring and in the winter, spring and winter. And then the wind bias is persistent all seasons. The wind speed bias is likely due to some higher roughness lengths in the MP table versus the veg palm table. The land model itself doesn't do anything to the friction or the wind. It takes things from the tables. So the only impact here is mainly through the table difference of the roughness length, where MP table does have higher roughness lengths, significantly higher roughness lengths than the old veg palm table that we use for NOAA. So these wind differences are not the land model per se, but just the tables that it uses. But it's an important thing to note that by changing the table values in NOAA, we can achieve a similar kind of improved wind bias. We may think of doing that in the future. And the profiles too, and NOAA MP has a lower PPL wind. This is again the green one. And the temperature profiles up here on the right, where you see the NOAA MP is a warmer daytime PBL, but less bias. And then the rainfall comparison briefly. This is back to all the tests listed here at the bottom. The only thing I would note here is that this slightly more delayed spin up is associated with the tests that have Thomson. Most of the default tests tend to have WSM6, but this Thomson does tend to show a slightly delayed spin up. But after a while, this is averaged over many cases for each season. So the rainfall is settling to the steady seasonal values for all these physics choices. So there are no red flags there. I'll hand over to Kelly because she has an update on the forum, and then I'll come back for questions after she's given this update. So Kelly, can you go ahead and give your update?
Jimy?
Yes.
Just a note, 3 minutes.
Okay.
Thanks.
Kelly's going to give a brief update, and then I'll come back for questions.
Okay.
Okay. Hi, everyone. I'm Kelly Werner. I am one of the members of the WRF support group. I just wanted to take a minute to tell you all about our plan to migrate our support forum to a new platform. We're currently using the PHP BB software and plan to move over to Zenforo, which is already being utilized by other NCAR support groups, and it has been found to be easier to use, effective, and efficient. The new system will have an updated look with a consolidated forums list or categories so that everything is better organized, cleaner, and easier to navigate rather than having to search through numerous sub-forums to find what you're looking for. The forum will also have better mobile responsiveness for use on mobile devices. It will include the ability to subscribe to certain forums, and users can be notified via email or on the web interface when new posts are added. There's an improved interface so that when one opens the forum, they will see all new posts first. There are updated search functions, and there's the ability to like posts, kind of like upvoting, which helps users to quickly find the solution on longer threads. We've already been doing a little bit of testing with this, and we've ensured that the new site will preserve all previous threads and attachments. So we do hope to clean it up a bit, for example, removing some duplicate content. And we've also ensured that all links will continue to work properly. The current plan is to open the forum to the public on June 23rd, but this will require a 2-day downtime for the entire forum system to allow adequate time for our system administrators to make the transition. And we will post this schedule as a banner on the old system just to let users know. So that is all, and I will hand it back to Jimy for questions.
Thanks, Kelly. So this is the summary of the main new features in the model, and I think we're open to questions briefly. I think we're already running out of time, but if any came up in the chat, or raise hands function is available too.
Okay, Jimy, a question. You showed NOAA has higher 10-meter wind speed bias than NOAA NP. What observations were you verifying against?
I think standard surface observations over the US. I'm not sure Ming may have that answer in more detail, but it was just the standard surface network, I believe. Ming, can you answer that? Is she there? Or Wei?
Yes, I think I can answer that question.
Yeah.
So for the verification, we compare with the GFS surface variables. We extract T2, Q2, and wind at 10 meter to compare with WRF simulations.
Okay. So it's just the analysis, right?
Yes.
Thanks.
Okay, another question, Jimy. Do you know of any plans to add GPU offloading to WRF in the derecho environment?
That's too detailed for me. I don't know of any formal plans with WRF and GPU. I think that will be MPAS is going more towards GPU.
Okay, Bill Skamrock has commented. He said, not at this time. So not at this time. Are there any plans to add GPU offloading to WRF?
Right.
Okay, there are no other questions in the chat, and we're at the end of the block. So Jimy, thank you very much. We'll proceed to the next speaker, and that's Dr. Jake Liu of M-Cubed. He'll be providing an update on WRFDA 4.4 and JEDI-MPAS 1.00. Okay, Jake.
You can see my slides, okay?
Yes, if you could put it in full screen mode, that'd be better. Yep. Perfect.
Okay,
Thank you.
that's good. Okay, good morning, everyone. I'm going to highlight some WRFDA changes in release 4.4. Then spend a bit more time to talk about JEDI-MPAS 1.0.0 release. So there are two major new capabilities in WRFDA 4.4. So one is we added GPS GMI reading state simulation capability. This was contributed by Dr. Dongmei Xu at the Nanjing University of Information Science and Technology. She also added some brief information in WRFDA 4.4 Users Guide for related name list setting and also the file input. So basically, you can download some file from NetCDF file from NASA website. Then you should be able to simulate this reading state. There is a publication related to this work. In version 4.3, we introduced aerosol chemical data simulation capability for WRF-Chem initialization. Previously, WRFDA can only work with two aerosol schemes, Gold Card and Mosaic 4-bin scheme were available in WRF-Chem. Now, Sung Yong Ha at NCAR also added a new option which made a VBS aerosol scheme when simulating surface aerosol observations. So now you have three aerosol schemes can work together with WRFDA and WRF-Chem. We also added a README file for the different options for aerosol chemical DA capability in WRFDA. So you can check more details, look into this README file. Another change is related to the atmospheric motion vector data simulation. When using NCAP buffer files, AMV data is also called satellite tracking. So historically, NCAP encoded all AMA data into the prep buffer file. But at some point, they changed their practice to assimilate a separate called setwin.buffer file for assimilating AMA data. They don't use any more prep bar file. However, they still keep encoding some of AMA data into prep bar file, even though that's not include all of AMA from different satellites. So in version 4.4, Jimy Brash at NCAR added a I/O interface to ingest satellite win.buffer file. So we can assimilate more AMA files that's not included in the prep buffer file. I should mention that we don't, the WRFDA does not read all AMA data included in satellite win buffer file. Instead, we just read some of AMA data in this file, not included in prep buffer file. So you have to read two files, prep buffer file and also set win buffer file, in order to assimilate a full set of AMA data. So there is a new name list parameter already turned on by default. If you don't have this file, it's still okay, just to give you some warning information, they can still run. I also like to make you aware of a bug fix for direct assimilation of radar reflectivity. There is a name list parameter called RF_Q threads. This parameter is supposed to be used by tangent linear and adjoint radar reflectivity operator. It was somehow also used by the forward operator. This could cause some unrealistic low bound for computed reflectivity from the model background if you set this value to a large number. The default value is not a big value, so this small shouldn't cause too much trouble, but somehow if someone setting this number larger value yourself, then you could get some problem. So we remove this, we remove the use of this parameter in the forward operator. So now this should be working properly. Meanwhile, we also simplify the quality control procedure when simulating radar reflectivity directly. So now we only keep observations with both observed and the background reflectivity value greater than a name list parameter called RF min. You can set this to 5 dBj or 0 dBj, whatever number you want. So basically, in setting this way, you will have not too much problem for so-called zero gradient problem when the background has no rain, at some locations. Even though this is not necessarily a best optimal setting, but I think this is a safer way to simulate radar reflectivity with a stronger nonlinear operator. So last year I mentioned we would release JEDI-MPAS DA system. So we made this happen last September. So JEDI-MPAS is a global regional unified MPAS DA system built on JEDI software framework. You probably know JEDI is a project led by Joint Center for Satellite Data Simulation. So basically, this JEDI framework developed several model agnostic data simulation component, including forward operator, data simulation algorithm, and background error covariance, etc. And when this component hook up to different models, so we will realize some model-specific data simulation system. So JEDI-MPAS is MPAS model hook up to those data simulation component. We also have some documentation, some tutorial as well in this website. So you can check this out. So this is an outcome of multiple year development with a project funded by US Air Force. Is a collaborated development between NCAR and the Joint Center for Satellite Data Simulation. For this first release, this slide lists the main features in this new DA software. So it can run, it can do both deterministic analysis and ensemble analysis. For deterministic analysis, you have three options: do 3D ENVAR, 4D ENVAR, and 3D VAR. So far, 3D ENVAR is mostly most extensively tested. Others should also working okay. It just we don't have chance to test too much. And for ensemble analysis, you can do ensemble of data simulation technique. So basically, you run multiple ENVAR analysis with perturbed observations for each member. You can run also in dual resolution mode. where the ensemble input and the analysis increment can be at a lower resolution than analysis in the background. That way, minimization can also run at a lower resolution, so that will reduce computational cost. Because JEDI-MPAS does the analysis directly on MPAS unstructured grid, it works for uniform mesh or variable resolution mesh, also global or regional mesh. So that's quite flexible setting. You can use the same source code and executable, it's just doing different setting. You can run with many different settings. One advanced feature with JEDI-MPAS is it allows all sky readings data simulation for some of microwave and infrared satellite sensors with hydrometers as analysis variables. And for readings data simulation, primarily based on CRTM. So we tested released the code with several month-long cycling experiments. This all using 3D ENVAR. So this is not a impact study, but using this month-long cycling result, we will know how this new system performs, is performed properly, this all capabilities working okay. So just show you some result in next several slides. So this here I will show 3 experiments result. So first one is named clear AMV. So this one will simulate conventional observation and a clear sky AMSO A readings. These 5 temperature sounding channels from 6 satellites. And the second one is called cloud AMSO AMA. So this one was simulating observation from the first one plus all sky over water AMSO A reading state from 5 satellite and also this 5 window channel reading state. The third one is further add clear sky MHS 3 watt vapor channel readings from 4 satellite. So this is month-long period from mid-April to mid-May 2018. This dual resolution 3D ENVAR at 30 kilometer resolution for analysis, 60 kilometer ensemble input. So localization both in vertical and horizontal. We also run 10-day forecast at each stereo TC. So just quickly show you some result. So here what I show is the RMS arrow of cycling background with respect to GFS analysis. And we compare second and the third experiment to the first experiment. Then we calculate relative RMS error reduction. So you can see for moisture field, this green curve is the reduction, negative means improvement RMS error reduction compared to the control experiment. So all sky MSO A readings have a large improvement at most of these levels. There are more than 10%, maximum can even reach 20%. And adding further MHS readings, you get a larger improvement at a higher level because it's weighting function from these 3 watt vapor channels. Temperature improvement is relatively smaller than compared to moisture. And the UV filter, you have also some large improvement because this mass wind balance implied in the ensemble data simulation. So looking into this RMS error reduction for 1 to 10-day forecast, you also see large improvement, up to 10% for the moisture field for this MHS experiment, This can even last for 10 days and with statistical significance. And the temperature improvement relatively smaller because this all sky readings and the MHS is more sensitive to moisture field. Also, you can see the UV field also U field also has some large improvement. And we also verify against this AHI reading state for cloud field. We have no much direct cloud observation, so we verify brightness temperature from AHI readings. This just show you this observed brightness temperature from Himawari AHI channel 9. They say for a time with 2 typhoons in the Pacific Ocean, and the right-hand side is the this radiative transfer model simulated HI reading state using MPAS 6-hour forecast at a 30-kilometer mesh. So you can see this is done pretty consistent between observed and simulated readings. So this from the solid basis, we can use this state for some verification of cloud field. And by the way, this you can see this low brightening temperature mostly there's cloud affected areas. So we verify this super-orbed HI readings. These super-orbed pictures basically match model resolution 30 kilometer. So with super-orbed observation with cloud detection algorithm, we can also separate pixels with clear picture, partly cloudy picture, and a fully cloudy picture. So you can see this RMS error reduction from these 2 readings experiment benchmark to clear sky readings experiment to 1 day to 10-day forecast improvement. So also has a large improvement for the day 1. You can reach nearly 10% improvement. Can also last for several days. And for cloudy picture, you can see there's smaller relative percentage improvement. But remember that cloudy area, so you will have a larger absolute RMS error. So that means you probably have a comparable absolute RMS error improvement. So last figure I show here is basically this ETS score for rainfall forecast scale verified against CMR for observations. So you can see I also add another curve. The black curve is no readings experiment. That's just a semi conventional observation. So adding clear sky readings, you can see a quite large improvement. Then if you add cloudy MSOA readings, have a further large improvement. Further add MHS, there's smaller improvement. If you see the relative root mean, not root mean square error, but GSS score, you will see 5 to 13% GS score improvement up to day 6 with some statistical significance. So just final 2 remarks. So WRFDA will be kept updated as needed. Even though we have no plan for future WRFDA tutorial, last year I already mentioned the last tutorial we conducted is in 2019. So we still welcome external user community developer to contribute. So we can incorporate your contribution into future WRFDA release. So we will continue developing update JEDI-MPAS. So we considering do a first tutorial of JEDI-MPAS in 2023 next year. Hopefully, maybe summer or fall time. It's just considering. So some of result is extracted from a manuscript recently we submitted to GMD. So later time you can check out it online once it openly available. Thank you. That's all I have.
Jake, thanks a lot. Very good. Checking the chat, we do not have any questions at this time. So it's the end of the slot. So if any questions come in, audience on this, or if you think of any, save them for the end of the session. Our next speaker will be Bill Skamrock, reporting on developing MPAS Earth System model capabilities. Bill, when you're ready.
Thank you, Jordan. Is that appearing now?
That's good. Full screen. Thank you.
Okay, I'm going to talk today about what we're working on in MPAS and what you'll see soon. Essentially, if you look, we haven't had a major release of MPAS in several years. The last significant release was the GPU-enabled version, which is a branch off of the main MPAS release. We don't have a regular release schedule as WRF does, so we release as we're ready. We have been doing quite a bit, though. In particular, I think what we're going to see in the following year in releases that we plan to do is, one, you'll see physics unification and updates to physics, and Laura Fowler is going to talk about this next. We're working on deep atmosphere extensions to take MPAS to geospace applications, so model tops around 500 kilometers. We have been working on LES extensions for MPAS, but that's not really ready for a talk yet, but we're getting there. What I'm going to talk about today is our work in bringing MPAS into an Earth system model, into NCAR's CESM, and I'll also talk related to that, to GPU development. But the other thing we've been doing, I just wanted to point out, is that we do have a real-time forecasting experiment going on associated with the Precip field campaign. That's a campaign that's centered on taking observations of tropical convection over Taiwan. And we're seeing results in that already at a variable resolution mesh, 15:3, sorry, it says 60:3, it's really 15:3, over with a 3-kilometer region over the Taiwan region. It's a fairly large region. And we're seeing results not asimilar to what we would see in the hazardous weather testbed results several years ago, in that there's skill in the convection and precipitation forecast out 3, even 4 days. And this is just an example of a particular case recently from that forecast experiment. That results from that experiment, real time, are available on the webpage given here, which unfortunately you can't navigate through to the MCube from the MCube page, but hopefully you will be able to soon. So our major effort recently over the last couple of years is bringing the MPAS dynamical core into the climate model here at NCAR CESM. And we're also looking to potentially bring in some of the WRF physics, particularly those we may need to get reasonable simulations at convection permitting resolutions, order 3-kilometer cell spacing. That effort goes by the name of SEMAS, System for Integrated Modeling of the Atmosphere. It's been ongoing for a few years now. And we're now getting to a point where we're testing inside of CESM, inside of CAM, which is the atmospheric component of CESM at convection permitting resolutions. I'm going to show you some of those results. The major issues we're trying to address right now is improving those results, as you'll see, but also we're running into infrastructure issues because CAM and the climate model uses a lot more memory than standalone MPAS does and costs quite a bit more, and we're trying to address those. I think we're going to have many of those addressed, at least in a reasonable manner, within this next, hopefully, 6 months or so. So I think we're going to see a release of this certainly before the next workshop next year, the hopefully in-person workshop. I also want to say a few words about GPUs. NCAR is bringing in a new supercomputer, Duratio. It has been delayed, supply line issues with computer parts and everything. We hope to see that before the year is out. I suspect it'll be open to general users early next year. Our intent is to release configurations of MPAS on this new machine. So, and we're also going to see significant updates to MPAS A as a result of, for example, more physics being brought in through efforts at NCAR and at other organizations. And we're also working to merge that GPU release with our main release branch. So those are the things you're going to see. So you are going to have available to you GPU capabilities somewhere in the near future in our release of MPAS. The other effort that's related to GPU work is an outside funded project by NSF, goes by the name of Earthworks, that's being led by folks up at Colorado State University, Dave Randall and Jim Hurl, and a number of us here at NCAR. And this is trying to bring that GPU capability into CESM. And here we're running all MPAS components, atmosphere, ocean, sea ice, et cetera, on a single 4-kilometer global mesh. That's our target. And we're hoping to get to a half a simulated simulated year per day by 2025. We're just in the process of bringing in the GPU components now and working on infrastructure issues associated with running very high resolution models. Our goal is to release this in 2025. It's a ways down the road, but it's already having input into the GPU capabilities of standalone MPAS, which is available. So we're going to see benefits from that well before the actual release 3 years from now. So as I mentioned, we're doing a lot of testing in terms of the capabilities at convective scale. We've done 2 sets of experiments. The first that are led by a project scientist up at CGG, Jinying Huang. She's been running variable resolution MPAS, the 60 to 3-kilometer mesh over the Western US, looking at the wet seasons, essentially November through March up in that region. And she's integrated essentially climate-wise over a five-year period, 5 of these wet seasons from 1999 to 2004, and has been looking at effectively the climate statistics of this. So that's the setup. And I'm trying to advance my slides here. Here we go. You can see the topography. I'm not going to show any results from the 60-kilometer run, but we will show also results from WRF that come from the Rasmussen et al. Study through that period conducted with a regional version of WRF as the topography depicted here on the right. So essentially the results, the top panel here, what you're looking at is the precipitation rate millimeters per day. And you can see that the version of MPAS running the CAM physics is a better match for what the observations, which come from Precip on a 4-kilometer mesh, are showing in the middle panel. And in the right panel, WRF tends to overdo it a bit in the Sierras, and that's where the improvement is primarily seen here. But what I want to point out here, though, is that the MPAS implementation running at 3 kilometers over part of the globe, at least, inside of CAM, CESM is running stably and robustly in that system and producing credible solutions. And if we look at the PDF of the distribution of precipitation intensities, you can see MPAS is in the red, the observations are in black, and WRF is in blue. We're following the 4-kilometer Precip observations somewhat better than WRF did in these simulations, at least in California and Oregon. And the errors in Washington, MPAS is a little low, WRF is a little high, based upon that set of observed precipitation statistics. We've also tested over the central US. We're just starting now. And that's the group here with an NCAR down in M-Cube, myself. Ming Chen has been doing a lot of work with this for me. And we've moved the 60 to 3-kilometer mesh to be centered over the central US. So essentially we're running, we've run standalone MPAS, and we've run MPAS in CAM using first the CAM 6 physics, which uses MG2 microphysics, which doesn't have a grapple or hail category. But we've also tested with the MG3, the Morris-Gettleman 3 microphysics, which has a grapple category. Both of those are double moment schemes. So that's there. And essentially, the initializations are identical for the atmosphere. For this case, I'm going to show you a very short one-day simulation is all I'm going to show here. But understand, we've got different physics, we've got different land models, and we've got different SSTs. But the atmospheric initialization, essentially the moisture and the dynamic state and the thermodynamic state, they are identical. So the results are shown here. On the far left is the reflectivity that's observed for this one-day forecast that's valid 27 April 2017. You're seeing a nice squall line propagating across the center of the country. That squall line has that beautiful strong convection and trailing stratiform region, and that comma shape, very nicely illustrated in that. If you look at the WRF physics simulation, it shows a similar character squall line. It doesn't extend the stratiform region quite as far south in Arkansas as you observed, but you see that leading line trailing stratiform structure. If you look at both the MG2 and MG3 simulations that are done in CAM with the MPAS die-core, you can see it really doesn't show that structure, that leading line trailing stratiform structure. It's just not there. We've done other tests which indicate that it's not the dynamics that are related to that or how it's configured, because we've done simulations where they're configured identically. It's either in the physics or the land model or the initialization of the land model. So something is going on here. And if you look a little more closely here, I've shown from the WRF physics run and the CAM MG3 run, here's the lowest model level of potential temperature, excuse me. And what you're seeing is you're seeing that sharp line where the leading edge of convection is, and that cold pool behind, and the cold front is well behind there, as you can see in the WRF physics run. You look over at the CAM run and you just don't see that strong cold pool ahead of the cold front, the large scale cold front. Essentially, everything is triggering over the front, and we're not getting a strong enough cold pool to force convection in the warm sector ahead of that front. And if you just look earlier at 18 hours, which is 12 noon before, well, as the line's getting going, and you can, what you see here is you see that the front in CAM is somewhat more diffuse than the front in the WRF physics. But this is not the MPAS die-core that's causing that diffusion. There's something in the CAM physics that's doing that. So these are the kinds of problems we're looking at in our implementation in CESM of the MPAS die-core, and trying to see if the CAM6 physics can give us simulations that are plausible. I'm hoping we're going to release that soon when we have good solutions to some of these issues. So just to summarize, we have a lot of development going on. You're going to see quite a bit of that development released pretty soon, both within the standalone MPAS release and hopefully within a release in CESM of MPAS. So that's what I had to say, and I'll be happy to take questions.
Great, thanks a lot, Bill. Question, it was actually answered by Wei, but a question while you were speaking was, why do you use IFS and not GFS? And the preliminary answer from Wei was that IFS is generally a better analysis. Would you concur?
Oh, not only is it better analysis, but you get better forecasts when we look at error measures of the forecast. So if you want to improve MPAS forecast, use the IFS analysis over the GFS if you have access to it.
Okay. Another question. Did MPAS force the WRF simulation?
No, that came from the GFS analyses.
Okay. That's it. No more questions. Sorry, one late question. What are the differences between MPAS and WRF simulations in their configurations?
Okay, so that I'd have to ask Xingying about that. I don't off the top of my head know exactly how that's configured. But actually, what you should, the WRF forecast come from the Roy Rasmussen's paper that is referenced in that talk. So you should go there to look at that. They did a long series of over many years over those seasons, essentially regional climate simulations. That is what we're comparing against. So you should go to that paper if you want to know the details or even contact Roy, and I'm sure he can point you to who could tell you more.
Okay, one last question. This will be it for this time. Does UPP support MPAS output for post-processing?
In principle, I'm not sure. We'd have to ask Michael Duda about that.
Okay,
If Michael's around, he can maybe answer it.
Jordan, this is Kate Pacell. I'm happy to
Okay.
answer that.
Go ahead.
It does not currently support MPAS native output. No.
okay, excellent. Thanks for that. All right, Bill, very good. We'll move to the next speaker. This will be Jordan Schnell from NOAA GSL, updating us on WRF Chem v4.4.
Alrighty.
We can see the slides. If you could get it in, perfect. That's in presentation mode. Take it away.
So yeah, thanks for listening. Whoa, that is not what I wanted to do. Thanks for listening, being here this morning. I'm Jordan Schnell, a research scientist at NOAA Series CU Boulder. I'm going to be talking about some of the WRF Chem updates since version 4.3. Starting with just some general updates, WRF Chem remains one of the most widely used chemistry modeling systems in the world, thousands of citations each year. The code management is back in the hands of NOAA, specifically at the Global Systems Laboratory. And so while the development of our NOAA priority development is with the FE3 DICOR, WRF Chem is still actively used for research. For example, the RAP-Chem experimental forecast model, which I'll mention a little later. NCAR does maintain oversight of some code, including the Mozart code, some input data and preprocessors, as well as oversight of overall WRF development. And I'll mention this again, but as many of you know, WRF is a community model, as well as WRF Chem, and so we appreciate any of your developments or bug fixes that you can submit. If you're not comfortable with Git, reach out to me or any of the developers or anyone on the release committee, and we're happy to help you get your code into the community version. A couple more specific bug fixes and enhancements since version 4.3. We had some changes to just the history stream for photolysis rates. Some were removed and some were added by default. There's a bug that in the vertical mixing routine inside the dry deposition driver where enhancement of the exchange coefficients were incorrectly done at the surface. There's a minor bug fix for extrapolation cases in the ME code. There's been some additions of different species to the RACM mechanisms for emissions, including HONO, terpenes, and CO2 that were not being read in, even though they might be in the emission files, as well as an issue that was corrected related to some Chem CV options. A few more enhancements. One, it was introduced in version 4.3 that is now fixed when using Mozart chemistry in conjunction with CU physics option 3, as well as convective wet scavenging. There's some code cleanup of the go-kart dust emissions when utilizing them with mosaic aerosol schemes. There's a new option now to couple subgrid boundary layer clouds from the MYNN PBL scheme to photolysis option 4 with a simple name list option. In addition, isoropia in chemistry options 100, 108, and 109, the RACM mechanisms is now controlled by a logical name list option and is off by default just due to some issues that some people were experiencing. Finally, unfortunately, there was a bug introduced in version 4.4 that we are aware about that does prevent users from compiling the model on the first attempt. And so there's two ways to fix this. One is just by issuing the compile command a second time. That should take care of the issue. Otherwise, you can modify the file listed here, which the presentation will be available online after the workshop for you to check this out. We do apologize for the inconvenience that this has caused. Some things in the pipeline coming for hopefully version 4.5. Specifically, I'll mention some things that are being tested currently in NOAA's experimental RAP-Chem forecast model that's built off of essentially wrap smoke, but it now has full chemistry that were from the WRF chemistry packages. Some of these include a new gas phase chemical mechanism. It's fairly cheap. It does a pretty good job at simulating ozone as well as other trace gases. The ability to ingest GFS ozone, both in terms of the full 3D distribution, as well as utilizing total GFS ozone in the photolysis schemes, including inline chemical mixing with MY and N. So by default, WRF Chem can only perform local mixing no matter what PBL driver you're using. Currently, the TUV photolysis module is only connected to Mozart mechanisms, but we're working on getting that connected to other chemical mechanisms as well. We're working on incorporating the Functia dust scheme, which is running in a couple different operational and experimental models being developed by ARL. The fire-radiated power-based plume rise algorithm, which is the feature in the WRAP smoke and HER smoke models, as well as the WRAP chem model. So this would be an additional option outside the traditional plume rise that is already in WRF chem. In addition, we're working on incorporating a pollen emission module that works similarly to the biogenic emissions, where you have essentially an emission potential that's modified online by environmental conditions. And as I said, all these developments are currently running and being tested in the WRAP Chem experimental forecast model. So I would like to just quickly highlight the pollen module that is being developed by Alison Steiner's group at University of Michigan. And as I said, it's being running experimentally in the WRAP Chem experimental air quality forecast model. And so currently there are 2 species being represented, primary pollen or PM10-like species, as well as sub-pollen particles, which are PM2.5 that are formed from the rupture of these primary pollen particles. There's also options to couple these to the microphysics with cloud-borne options and extensions beyond just the simple single pollen type tracers, so additional species. This is working with the MAID sorghum aerosol scheme. And so, yeah, just to quickly again plug this WRAP Chem experimental air quality forecast model that's running in NOAA GSL, has been for the last couple of years, where we're really utilizing this to test new developments that we hope to get into the community version of WRF Chem, as well as potentially some of these packages being moved into an operational sense for NOAA's next generation air quality forecast models. So some applications of WRF Chem that I'd also like to highlight. The WRAP and HER smoke models, which went operational in December of 2020. The WRAP smoke products have actually replaced the high split smoke products at NCEP, just due to their how great they've been doing. And so if you live in anywhere that's been impacted by smoke, you've probably seen graphics coming out from the HER smoke model. This is all made possible by WRF and some of the WRF Chem packages. And so you can access any of these forecasts at the websites listed below. One thing that the HER team wanted me to mention was a new diagnostic product that's made available for HER smoke, as well as will hopefully be in the new Rapid Refresh Forecast System, or RUFUS. And so this is just based on already outputted diagnostics from HER smoke, but then go into an empirical function to create this hourly wildfire potential that's being tested. And so in addition to the HER smoke and WRAP smoke and WRAP Chem models, we're hopefully going to be here at NOAA GSL producing a HER Chem model, so similar to the WRAP Chem, but just on the HER grid. So it would be a 3-kilometer full air quality forecast model. So hopefully you guys can check that out soon. In addition to all of these other forecasts that I've mentioned, many other groups around the world are using WRF Chem for their air quality forecast. NCAR, no surprise, is using it. They have 2 forecasts being operated. One is the FireX-AQ and another experimental forecast called AQ Watch. Both of these are at 12 kilometers, a 48-hour forecast being run once a day. I know the FireX-AQ data is available for download, and you may be able to access the AQ Watch data as well. Just in addition to NCAR, there's, like I said, all these different groups around the world that have found WRFChem very a useful tool in using it for their air quality forecasts. So speaking of tools, there have been some updates to the WRFChem tools. One, the EPA Anthro EMIS tool. And so this allows the use of the smoke processing system that's developed by SEMAS and EPA. Those emissions to be utilized in WRFChem. There was a small bug fix that was corrected in that tool. A new version of the FIN fire emission and inventory is available, version 2.5. The Edgar V 5.0 emission inventory is now available in Mozart speciation for use with the Anthro EMIS tool. The lateral boundary condition processor MOSBC code is now available for the new WRF hybrid coordinate system. And then two other tools that are not necessarily operated by anyone at NCAR or GSL, but I'd like to mention. One is this MERA to BC interpolator, which allows MERA 2 reanalysis products to be used as initial and boundary conditions for the WRFChem simulations. And then another is this Hermes emission modeling framework tool. As we know that emissions are kind of one of the pain points for many users in generating them and deciding what processors to use and that sort of thing. And so Hermes seems to be something that users are appreciating and using quite well for multiple different inventories. Another tool that's recently been made available that's is not maintained by NCAR, UCAR, or NOAA GSL, but was developed by an individual user in collaboration with some others. Will Hathaway, which is this install tool, which essentially determines the needs on your system and does all of the work for you, installing either WRF by itself or the full WRFChem with the kinetic preprocessor. In addition to potentially WRF Hydro, if you're interested in that. Works on a number of different systems and installs all the libraries that are required for the different installations, as well as options to install a suite of pre and post processor tools. So this is something that seems to be quite appreciated around the world as people are having trouble figuring out exactly what all is required to install these packages. And so this has been something that you can check out. Another tool being developed is called Melodies Monet. So the primary developers of this are Rebecca Schwantes and Barry Baker. This is essentially a model evaluation toolkit that works very well with WRFChem, but it can also be utilized with other models, including CMAC or FE3 models. Currently, it's mostly limited to comparisons with EPA air now surface sites. I'm personally using it to compare near real time the RAPChem forecast, as well as several other operational and experimental air quality forecasts against EPA observations. I will mention that this is still in the major development phase, so it's nothing. If you do find an issue with it, that's potentially expected. It is, like I said, under development still. However, the developers are very much encouraging those of you that are interested to try it out, see any problems you might be having with it, or any suggestions you might have. And so you can find this at the websites listed down below. We do have a kind of a community development sheet, so just a way for those of you that are interested in contributing to WRFChem, just a way to facilitate that collaboration, to see what's planned and what's ongoing, and where not being able to reinvent the wheel type of thing. And so this is something that if you're interested in, just please shoot me an email and I'll get you access to it. Final few important notes. The user guide has been updated to version 4.4. Please sign up for the WRFChem discussions email group. However, if you do, please include your name and affiliation so I know that you are not a bot. We receive dozens of requests per day anymore from what I believe are spam accounts. So if you don't include your name, you will certainly be rejected. As was mentioned earlier, please use the new use the WRF forum for WRF-Chem related questions. There is the new one that will be released here later in June. And again, at any time, if you're interested in contributing to the community code, please reach out to me or someone else on the development team. We'll be happy to help you get your code into the community version. Presuming it doesn't break anything else that's already in there, but we're very interested in seeing developments by the community make it available to the community. And so the future of WRF-Chem, NOAA will continue to support and maintain the WRF-Chem code, though, as I said, most of the major efforts focusing on the development of the FE3 based models, while some schemes that are currently in WRF-Chem will also be put into these FE3 based models through the Common Community Physics package. NCAR will continue to use WRF-Chem for research, though most of their major effort is focusing on Musica. But all that said, have no fear, WRF-Chem is here to stay. I'll just leave up a couple of these websites. Again, you can find this presentation that'll be available online after the workshop. And with that, I'll end and take any questions you might have. Thank you.
Jordan, thanks a lot. We have time for one question, and there is one question or two questions. The first part, does WRF-Chem pollen include particular pollen variables or just their size, like PM10, et cetera, for physics?
So the current version we're using is yeah, it's not based on any particular plant species. It's a primary pollen, and you can modify the size that that they're given. It is I believe it corresponds with about the 4th bin of go-kart, so it's actually slightly bigger than PM10. But that's user controlled by many different ways in terms of just modifying the radius and density of that species itself. Not sure when it'll be in the community version. We'll hope to be version 4.5. I know Professor Steiner's group is really interested in getting it out to the community, but it's nice to be able to test it now in a real-time sense.
Thanks. And the last question is, and I could probably answer this as part of the release committee. What's the timeline for WRF-Chem v4.5? Jordan, would that just come out next spring with the rest of WRF v4.5?
Yeah, I would say that's the plan. Is it's typically been about on an annual basis, with around end of April being the last, I think, 3 releases or so. So yeah, I mean, I won't be the one to say that, but I guess that's what it has typically been, is end of April of each year is when the major releases, with about 2 to 3 minor releases sometime in between.
Yeah. So tentatively, that's the schedule, next April. Okay,
I would guess so.
Go ahead. All right. Thanks a lot, Jordan. We'll move on to the next speaker, Wenfu Tang. Wenfu will be speaking on Musica.
Can you hear me okay?
I can hear you. We can see you. You can start your slides.
Okay. The other user need to stop sharing. Okay. Okay.
Good. We can see your slides and they're full screen. So thank you very much. You can begin.
Yeah, thank you. Hello, everyone. I'm Wenfu Tang from ACOM at NCAR. And today I'm excited to be here to share with you the new modeling capability called Musica. And before I start, I'd like to acknowledge all my co-authors as listed here, and all the people who contributed and are contributing to the development of Musica. So what is Musica? So the multi-scale infrastructure for chemistry and aerosols, it will be a new model-independent infrastructure which will enable chemistry and aerosols to be simulated at different resolutions in a coherent fashion. And most importantly, Musica is to be developed collaboratively with university and government researchers, nationally and internationally. Therefore, your contribution is valued and welcomed. And here I would like to introduce to you the vision of Musica. And this figure on the right shows our goal for the structure of Musica. First of all, The vision for Musica is to have a modular framework that facilitates the use of a variety of chemistry schemes, physics parameterizations, and atmospheric models. And it is also coupled to the other Earth system components, such as land, ocean, and CS. Therefore, Musica can be used to study the interactions between atmospheric chemistry and other components of the Earth system, and also climate. And in addition, Musica also includes the whole atmosphere. Therefore, you can use it to study the stratosphere and above, and their interactions with the troposphere. And in addition, Musica has the choices for variable resolution grid. And here are two examples. On the left, I'm showing the Musica with the spectral element dynamic core. And on the right, I'm showing the Musica with MPAS. And because of the capability for variable resolution grid, Musica allows for the simulation of large-scale atmospheric phenomena while still resolving the chemistry at emissions and exposure relevant scales. And because Musica is a global model, here I want to emphasize another advantage of Musica, which is that there is no need to deal with the boundary conditions to study a region at high resolution. And we can simulate global impacts and interactions in a consistent and a coherent way. And to demonstrate these 2 points, here is an example. This video will show the Musica model traces of carbon monoxide emitted from the fires within the corners. And this case is for a major fire event during summer 2020. And I also overlaid the domain of NCAR WRF operational run as shown by the white line in this video. As we can see, the CO emitted from the western fires, they took a trip outside the WRF boundary and then came back and impact the air quality in the eastern US. And if we want to understand this process, we will need Musica to do this. Otherwise, the CO will simply leak at the regional model domain boundary. And here is another example. This map shows the temporal variability of free troposphere ozone in summer 2020. And the variability is high over this region. And on the right is the O3S from Musica, which demonstrates that the high temporal variability in that region is due to the stratospheric intrusion. And besides, there are also other advantages of Musica. For example, for the shown simulations, the computational cost of Musica is similar to WRF, and Musica is fairly straightforward to run. If you can run WRF, you can run Musica. And in addition, there are plenty of user resources online you can find, such as the wiki pages, the recorded tutorials, and of course, you can always approach us for support. And now that we've talked about what is Musica and why do we want to use Musica, here I'd like to present you the Musica version 0, which is already available as a configuration of CSM. And here is a standard grid for Musica version 0 with regional refinement over the corners. So to demonstrate the value of Musica version 0 at the regional scale, we would like to show you that the Musica version 0's capability of representing the regional scale features is comparable to that of regional models. So for that purpose, we compared Musica version 0 simulation with 2 WRF simulations that have a resolution of about 12 kilometers. And the Musica and WRF results are from the optimal configurations for each model. And therefore, they have differences in the emissions and the physics, and also slight differences in the chemical mechanisms. Therefore, the comparisons of the absolute amount is not shown here, and we will show the model variability. And I will only show a few comparisons today for the sake of time. Let's look at precipitation first. Here I'm showing the distribution of the temporal variability in precipitation from MUSICA on the left and the WRF on the right. And besides the West Coast, the temporal variability in the two models are similar. And in addition, this figure also shows that there are issues on the WRF domain boundary because the temporal variability near the four edges are very high. And here I'm showing the spatial variability of precipitation in MUSICA and a WRF simulation at different spatial scales. Each panel is to show a spatial variability at different spatial scale. And as we can see, the spatial variability in precipitation of the two models are comparable at all these shown scales. In addition, at the spatial scale of the quarter degree, MUSICA shows even higher spatial variability than WRF. And here I'm showing the spatial variability of ozone in MUSICA and two WRF simulations at different spatial scales. The first box in each panel is MUSICA, and the other two are WRF. And the top row is for free troposphere average, and the bottom row is for the PBL average. And same as before, each panel is to show spatial variability at a different spatial scale. And as we can see, MUSICA can represent the regional scale variability reasonably well compared to WRF. And here is the same figure, but for PM 2.5, and the conclusion is also valid for PM 2.5. And here I'm showing the distribution of temporal variability of ozone. The top row is WRF, the bottom is MUSICA, and on the left is free troposphere, where on the right is PBL average. And overall, the spatial distribution and the magnitude of the temporal variability from the two models are close. And as we have seen before, the difference here in this region is likely due to that MUSICA has a better stratosphere conditions, which is important for stratospheric intrusion. And here is the same figure, but for PM 2.5. The conclusion is also valid here. And the difference over the Pacific Northwest is likely due to the difference in fire emissions. I have only showed a few cases in the WRF and MUSICA comparison, but the conclusion is that the MUSICA version 0's capability of representing the regional scale features is comparable to that of WRF. And with that being said, here are a few examples of the current applications of MUSICA version 0. And there are CONUS grid, Arctic grid, Asia grid, and Africa grid. And here is an example of a high resolution grid over a relatively small region. And specifically for the Arctic grid, we are planning to run the MUSICA model recently and provide the output to whoever would like to take a look. So if you are interested, please let us know. And a full list of the current available grid can be found through this link. Please take a look at this list, and if there is an existing grid that fits your need for your interested region, that can save a lot of time to start with. And if there is currently no existing grid yet for your interested region, I consider that being a great opportunity, and we welcome your contribution. And finally, the last part of this presentation is about going to higher resolution. So our current modeling system at NCAR utilizes multiple models with different infrastructures when dealing with different scales. And as mentioned previously, we are now moving to one infrastructure that will allow us to configure the models for local to regional and to global scales. And we have talked about MUSICA version 0, which uses hydrostatic dynamic core. And moving forward and going to higher resolution, MUSICA version 1 is now being developed and tested. MUSICA version 1 will use the MPAS, a non-hydrostatic dynamic core. And here on the right is an example to demonstrate that. Please visit our website for more information. And now I'll stop here with the take-home messages. Musica is a new model-independent infrastructure which will enable chemistry and aerosols to be simulated at different resolutions in a coherent fashion. And the Musica version 0's capability of representing the regional scale features is comparable to that of WRFCam. And most importantly, Musica is to be developed collaboratively with university researchers and the community, nationally and internationally. Therefore, your contribution is more than welcomed. And I would also like to mention that the Musica tutorial is freely available online without requirement for registration. And the slides, the practice materials, and the videos are all available through the link here. And I personally found that being very useful and easy to follow. And feel free to reach out to me or anyone on the Musica team. And I'll stop here for questions. Thank you.
Wenfu, thank you very much. There's one question so far, and I think you started to answer this, answered it in part at the end of your talk, but you can answer it again now. Does Musica support higher spatial resolutions than 12 kilometers? Is it possible to use it at 3 kilometer resolution comparable to 8 Her smoke?
Yes, in fact, Dusang Zhou from ACOM is doing analysis over Korea using the 6 kilometer, and the MPAS, the Musica with MPAS dynamic core will be able to go to even higher resolution.
Okay. Another question is the questioner would like to know which scheme is used in this particular experiment for comparison.
Yeah, that's
perhaps the WRF Musica comparisons. What schemes were used?
So for Musica, we are currently using the default CAM and CSM schemes. And for WRFCam, I will need to check with Rajesh Kumar, who conducted these 2 WRFCam simulations.
Okay. All right, thank you on that, Wenfu. Okay, Wenfu, thank you very much. There are no other questions. We'll move to our final talk of this session, Laura Fowler of NCAR, discussing the shared physics repository for WRF MPAS and CM1. Laura, very good. We can see your first slide. It's in full screen mode, so you may begin. We cannot hear you now. Wei, are you there? Can you hear?
Okay, better?
Oh, yes. Now we can hear you. Thanks, Laura. You can start.
Oh, okay. Looks like I muted myself. So as I was trying to say, I'm going to talk about the status and motivations to develop a shared physics repository between WRF MPAS and the cloud model version 1. And this talk is in collaborations with a few members that work at MCube, Gretchen Mullendorf, George Bryan, Michael Duda, Jimy Dudhia, Wei Wang, and Mei Wang. Let's see. Looks like I cannot advance my slide.
Move over to your lower left, see if you can. There's sometimes there little.
Oh yeah, let me use that button instead. That makes sense. Okay. So we want to first develop a new infrastructure to facilitate the physics implementations and interoperability of physics between different models that are originally being developed and currently maintained at MCube. So that includes WRF, MPAS, and CM1. So we're going to have these new infrastructures built on a set of physics parameterizations that are going to follow some coding standards taken from the Common Community Physics Package, also known as CCPP, and built a shared with physics repositories that are going to contain those different cleaned up physics. So the main goal is to remove the dependency of the WRF coding structures on those physics parameterizations. So if you have the WRF model, MPAS, CM1, or later on, you can have a different host model. WRF physics were initially developed and tested specifically for WRF. So for instance, their implementation in MPAS is pretty tedious because you have to the MPAS structure, coding structure has to adapt to the WRF coding structures, which implies that we need to add some interstitial subroutines between the WRF physics and MPAS so it can be work correctly. Same with CM1 and other host models. So we want to reverse that process and remove the dependency on those physics so they are not so WRF centric. So now we want to, the plan is to design a shared physics repository with individual physics being void of all WRF centric structures that will conform to some of those CCPP standards, and that can be easily accessed back to those different host models. So updating MPAS can be a tedious process, which is one of the reasons why we do not have physics that are immediately and systematically updated to the latest WRF release. If I take the different parameterizations that are available in the Mesoscale reference suite, which is also the tropical suite in WRF, and they are listed here on the left, in this left panel, the right panel shows now the release version, their corresponding WRF release version. So if we look at the RTMG and radiation scheme and the NOAA LSM scheme, their release are about now 4 version past that of the current 4.4 version release. YSU and WMSM6 are now from the version 4.2, whereas the gravity wave drag over orography or the NTITCO schemes are more in sync with the current WRF release. What's interesting, for instance, here is that the convection scheme, the NTITCO convection scheme, has actually updates that haven't been fed back into the WRF release. So there is definitely a mismatch between in the WRF release version between the different parameterizations, and sometimes we can also have a mismatch between the two models. So we are trying to kind of remove those discrepancies. Once updated, also, another motivations to do this work is that once updated, the MPAS physics is not always rigorously tested at global, regional, and cloud scale, because we do not have at this time a set of robust regression tests that are systematic and will really help us speed up that process. So the paradigm has been a little bit that if we trust that if updates are good for WRF, then updates are good for, which is a limited area model, then updates are good for MPAS as well, although it is a global model. So we need to develop a set of regression tests, which is also part of this project. Regional MPAS is a great tool for comparisons against WRF, and as well as for finding and fixing some bug fix in global MPAS. Here I'm showing a map, global distributions of the annual maximum snow albedo, and you can see that in the current default version of MPAS, that maximum snow albedo is actually set to 0 over sea ice point, whereas in WRF and it is actually equal to 0.75. So comparing regional MPAS against WRF help not only the forecast using MPAS, but as well the initialization. And the reason is because sometimes it is difficult to go through the complexity of the WRF model and be able to translate that to MPAS. Finally, the last motivations to do that is that, as I said earlier, MPAS physics drivers are very much WRF-centric. They use the same dimensions for the local arrays, the order of the array index, and that leads to lengthy drivers and sometimes overheads. We have an extensive use of those for simplicity, we have developed those from MPAS and to MPAS interstitial subroutine that are not really needed, since in MPAS, we can definitely drop that J dimension, which always appears in the WRF physics. So looking back at some past WRF MPAS workshop, I found at least 2 talks that kind of actually talked about the community physics package. So that project started in earnest about in 2018, and one of the first talk was given by Gettleman in physics on single track physics. So other NOAA, NCAR, other agencies like the Navy started to collaborate on the development of what they originally called the Common Physics Framework, CPF, which is now referred to as the CCPP, and I provide here the URL for that project. So they outlined a few of the basic principles, which was to build a set of physics parameterizations that would conform to selected standards that can be easily implemented in different models developed at NCAR, NOAA. For instance, NCAR would be CSM, MPAS, and WRF. So in essence, they would be agnostic to the dynamical core and independent to that core. And they also kind of wanted to have it scale insensitive for applications in weather and climate. Furthermore, the different host model then would be responsible for the interface between the parameterization itself and the physics drivers. The second talk I found was more recent. It was given by Dave Gill on at the WRF MPAS workshop in 2020. And it was about sharing, specifically about sharing physics between WRF and MPAS. And this is one of the slides that he discussed in his talk. So if you look at this panel on the left, it kind of describes the typical original interface between physics here and a host model. So for WRF, MPAS, and other models, we basically have different physics drivers, and each driver corresponds to a specific physics process. It can be convections, radiations, land surface scheme, cloud microphysics. Then there is what I would refer to as a mini driver, which is actually the top layer of the physics scheme. And then you go down one level below, and then you actually get to the actual parameterizations that describes the physics process itself. And you repeat that for the separate drivers. So right now, if you think of MPAS, we have to add those interstitial layer at the top of the top layer of the physics scheme. In WRF, we have the top layer of the physics scheme and the worker layer of the physics scheme that are actually bundled in one file, one module or source code. And therefore, MPAS is forced to kind of adjust its own structures to what the physics, the top layer of the physics scheme wants to see. The 2 panels on the middle and the right panel now show how the use of the CCPP would allow the simplifications of this scheme here. What I want to point out is that in these 2 panels here, we retain the worker layer of the different physics parameterizations. And it is those worker layers physics schemes that are going to be shared and implemented and available from the shared physics repository. Each physics scheme will also have a data file that will contain the descriptions of the different variables contained in the argument list to ease the implementation of that specific physics. The rest is going to be completely dependent upon the host model itself. So the host model interface will be different for WRF, MPAS, or any other model for that matter. Go here. So where are we? We are presently focusing on one suite, and that will be probably expanded to the other suites available, to the other suite available at MPAS currently into additional new physics parameterizations. We are focusing on the so-called Mesoscale reference suite in MPAS, also known as a tropical suite in WRF. And outside of the land surface scheme, those parameterizations are listed in those two boxes here. So we have updated in MPAS those different parameterizations to the WRF release 4.4. And a few months back, we did start to kind of modify those parameterizations so they kind of are CCP compliant, meaning that they have adopted the coding standards that was developed by the CCPP. So if you look at this panel here, I'm going to describe that's an example of the file that contains the gravity wave drag parameterizations over orography. This is basically the file that's available in the WRF release right now, and it contains the top layer that I described earlier, and the actual worker layer, which is the actual parameterizations of the gravity wave drag over orography. So the two subroutines that is called by the WRF or MPAS driver, that's subroutine GWDO, which is a 3D subroutine, which is self-called a 2D subroutine, the GWDO2D. So in MPAS, we do have extra interstitial source code here that helps kind of bridge what the MPAS structures need to run that specific parameterization. So what we have done is that we did split that bigger file into two smaller files. The first file, this first box here describes that contains the top layer of that earlier source code. We kept the name module_BL_GWDO. So, and that's part of the parameterizations belong to the host model itself. And now we have CCPized the second part, the worker layer, which is the actual parameterizations of the gravity wave drag. And we just simply rename some of the subroutine. And it is all these specific parameterizations that are going to be shared by the in the physics repository, shared and accessed by the different models. So in conclusion, we are currently developing a shared physics repository, which is going to be a GitHub repository. It is only going to contain thoroughly tested scheme, and we're going to organize those different schemes as a suite, just as I explained, like initially the Mesoscale reference suite or tropical suite in WRF. And each scheme itself is going to be completely agnostic from the host model and void of a model-centric source code. We're going to be able to, the shared physics repository will be downloaded at compile time to the host model using the CSM external management utility managed external, and I give a reference here. Right now, we think that we're going to have two branches, a main branch that is going to contain quote unquote frozen scheme that is going to be used for the major release, and a development branch that may contain new physics that may be moved later to the main branch, or physics that can also contain updates of physics parameterizations that have been implemented earlier in the main branch. We probably will make use also of a tag that will keep track of the state of that shared physics repository relative to the host model and how compatible they are with the different host models that will access that shared physics repository. So we are moving along with this this project. We think that by the end of the year, we're going to be able to have a good first version of that shared physics repository. And before I conclude, I also want to mention that we at this point, we certainly don't have the plan to move all of the WRF physics into the shared physics repository. And we kind of invite developers to kind of participate to that project as well. Thank you.
Thanks, Laura. I will check the chat. There are no questions right now in the chat, but I have a question about the managed externals. Will that be able to be run by itself, or will the SEAM infrastructure be necessary to have prepared and operable to manage the externals?
Well, let's see. I hope that Michael Dudhia can quickly interrupt me if I'm wrong, but the managed external tool will sit at the top of every host model, because it kind of also makes use of an external file that is going to be host model dependent, depending on where the host model wants to download that specific shared physics repository and the version of the shared physics repository that it will need to download. So as for other models, I think like FV3 and definitely CSM and other model, the managed external tool will be available directly from the host model. If that,
Okay.
I hope that answered that question.
Yeah, that's good. Here's a question. What are the requirements if I want to have another model that is not WRF or MPAS make use of the CCPP? So what are the requirements if someone wants to have another model use CCPP?
Well, I mean, we definitely want to, well, the way we have been going about right now is that the parameterization itself has to be 2D, has to be kind of void of, model-centric source code, so it can be easily transferred to other models. And I think the best way to answer that question is can actually provide an example of what the CCPP wants to see, or what we think, I mean, what we would like every parameterizations to look like to be able to access that shared physics repository or add physics parameterizations to that repository.
Okay. Good. There are no other questions, Laura, so thank you very much. Oh, wait, sorry. One last question came in, and folks, this will be the last one. There are actually two. The first part of it is GWDO important while using the Mesoscale reference suite for coarser resolutions? Is it important to run GWDO in the Mesoscale reference suite if you have a coarser resolution?
Well, I haven't done a specific test to see if it's important or not, but I think you definitely want to kind of, depending on the resolution of your model, I mean, you might as well just keep it on, right? Turn it on. So, but I haven't done any specific test with or without the gravity wave drag or orography to kind of test the difference in forecast with or without it.
Okay. Yeah, I understand your answer. And there was a late question, but we'll just give it to you. The questioner is checking, the WRF physics will soon be added to the shared physics repository?
Well, I think I would phrase it the other way around, right? The shared physics repository will be added to the WRF structure. Okay. And so there is going to be a little bit of a, not reshuffled, but some of the top layer driver will remain in the physics, but those top layer drivers will access that shared physics repository. Yeah. So it's going to be added to wherever WRF developers, well, not no, where the WRF developers decide to access that and put that shared physics repository.
Yeah, I think part of the query is about the number of physics packages that will be in the shared physics repository, the number of WRF physics packages, because WRF has so many. Because the follow-up part was, would a multi-physics ensemble currently run with WRF also be available for MPAS? So WRF has so many physics packages, you can run a multi-physics ensemble with it. If there's shared physics, will all those physics options be available to MPAS?
Well, initially, I mean, that's what I was saying earlier. I mean, there is not really any plan to implement all the physics parameterization that are currently available in WRF to the shared physics repository. But in terms of ensemble forecast, depending on so those specific parameterizations, it could certainly be part of that shared physics package for ensemble forecasting for using MPAS as well. That kind of depends a little bit on manpower and who is willing to kind of help us out to modify some of those fixed parameterizations so they kind of follow the CCPP coding standard.
Yeah. Okay, Laura, thanks again. That's it. Wei, I'll turn it over to you.
Okay, so we're running a little bit late. Jordan Chanel, if you're online, I propose we come back in about 5 minutes. Is that too soon for, yeah, so that we can catch up some of the, overtime. How about, yeah, about 5 minutes. Thank you. Sorry. Pedro, are you there?
Did you ask if I'm here?
Not you, Pedro, the first speaker.
Oh, Pedro. Okay.
Pedro, yeah. I saw him earlier, but he might.
He's here. He's maybe not like sitting at his desk right now, but he's joined.
Yeah. Pedro, if you can hear me, you can start preparing, sharing your slides. Because we don't have
I sent him a private chat. I don't know if he'll look at it, but if he does, he'll know to do that.
Yeah, he should hear me if he's
okay.
Yeah, I hear you now. Good. Yeah, if you can bring up your slides. Let's see. Yeah. Thank you.
Fine.
Jordan, we can try to start 11:06 or 07-ish. That's true.
Sounds good.
Thank you. Good, it's up. Can you make that full screen? Good. Can you advance it? Can you move it to the next slide? Yes, then you're all set. Leave it there. That should be fine. Thank you, Pedro. Yeah, just leave it there. Then we'll start in a few minutes. actually, Jeff Wilson, are you on? Okay.
Go ahead and get started, I guess.
Please go ahead. Yeah.
Okay, welcome back, everyone. Hopefully you've had a chance to grab a coffee or do what you need to do in the break there. This is session 2 of the model development updates. Just a reminder to everyone to please mute yourself if you are not presenting or actively asking the questions. Please reserve them till the end of the talk. You can either do the raise hand function or just put them directly into the chat. We'll get to them. If they're not, we don't have time right after the talk, we'll answer them at the end of the session. So we are going to start off with a presentation by Pedro Jimenez on recent additions to the WRF solar model. So go ahead, Pedro.
All right. Can you hear me well?
You can.
Right. So I'm going to provide a description of 2 recent additions that we introduced into the WRF solar model. The first one is the WRF solar ensemble prediction system that has been designed to provide probabilistic forecast with WRF solar. And the other is the MATWRF short-term prediction component that, well, obviously, the aim is to contribute to short-term solar irradiance forecast. I would like to thank the many scientists who have contributed to these developments, the WRF solar team. Let me start with the motivation for adding these developments. The beginning of WRF solar, at the beginning, we focused on the physics, and in particular in the improvements of the cloud aerosol radiation feedbacks. And we were lacking an ensemble prediction system or a probabilistic forecast component specifically tailored for solar application. And this is useful because it allows us to quantify the uncertainty in the estimations. And this is relevant, for example, for day ahead predictions, solar energy predictions. And with WRF solar EPS, we are filling that gap. The second thing we were missing is we were lacking a cloud initialization component. And this is relevant for nowcasting applications. We need a good cloud analysis. We need to know the location and the hydrometeor content of the clouds in order to provide a good solar irradiance short-term predictions. And here I highlighted that we not only need the good analysis, but we need to keep the clouds in the model. If we don't have a good environment, they may dissipate quickly. And in this direction, in this second point that I hear, the third one, is where MATWRF is contributing. So in the presentation, I'm going to focus on these 2 components, WRF solar EPS. I will provide some detail here. Jimy already mentioned some of them. Here I will introduce a few more. And then on Thursday, there is another talk from Yuhe Kim that it will go into more details of the model and show a comprehensive comparison against observations. And in the second part of the talk, I will focus on the MATWRF model before I conclude with the summary. So the WRF solar EPS model has been a collaborative project between NCAR and NREL. And here on the right, you see the diagram of the development. So how did we put together the model? And I like to split it in two parts. The one I highlight in red is the development. And here we identify the variables more relevant for solar irradiance predictions from a selected set of modules. And then we introduce stochastic perturbations in these variables in order to get the probabilistic system. And we identify these variables using a tangent linear approach. This is frequently used in data simulation. We apply for identify sensitivities in variables. And you can see here there's a publication summarizing main findings. And then in the second part of the development is the assessment, where we run World Solar EPS and compare it with observations and even calibrate the ensemble. And this is what is summarized in this other publication that I highlighted here. And also, as we saw in Jimy's presentation, is World Solar EPS is available in the in Word version 4.4. These are more technical details about how to use it. And we have a configuration file in the run directory, and it includes the 14 variables that we identify with our tangent linear approach, and some characteristics of the perturbation, the amplitude of the perturbation, the spatial scale, the decorrelation time of the perturbation, and other variables. In principle, we can use these values, but the user, if it finds other values more appropriate, this can be changed. And then on the other part that the user needs to modify is the word name list. In the stoch block of the name list, we turn on World Solar EPS by setting multiperturb equals 1. Then this is an entry to initialize the random number, the random numbers. So it has to be different for each ensemble member. And then there is another variable, SPDT, that controls how frequently we update the perturbations. By default, it's every time step, but this hurts performance. So you can increase that to 5 or 10, and that should be able to provide good results without hurting performance so much. And then the user can select which modules, for example, here we say activate farm perturbation, and which variables within this parameterization we want to perturb. So the user has total flexibility to select, to configure the variables to perturb and the characteristics of the perturbations. And a full list of the World Solar EPS entries are available in the readme.namelist file. This is an example of one run of the model. And for this case, you can see that in the first day, World Solar EPS is in green. Is very confident, it's going to be clear. Here we are missing this cloud event. In the second day, that is more relevant. Here we see the clouds. There are more clouds. This is the irradiance, what I'm showing here in the shaded one are the observations. You can see in green, World Solar EPS is the spread is not very large. It's under dispersive in this case, and we found this is generally the case. And with the calibration, and this is an example with an analog-based methodology, we can increase this spread. Again, this is just one example, and I encourage anybody who wants to know more about World Solar EPS to attend the presentation from Juhe on Thursday. I'm going to switch now to the second part of the talk, the MathWorks model. Main focus is in short-term predictions. And with MathWorks, we combine our previous experience with two nowcasting models. The first one is MathCast, that is a satellite-based nowcast system that uses the radiances from the satellites to retrieve the cloud fraction and advect it with our physics. And the other model is World Solar, that has better physics and is tailored for solar application. So when we run these two models, we saw these typical errors that I saw here. In red is MathCast, that they typically tend to grow linearly and with the lead time. And then at the initialization time, MPAS were usually better than World Solar because of the initialization component. But after certain time, about 1 or 2 hours, the errors between the two models cross. And with MathWorld, we had the idea to combine these two ideas into one single model to benefit from both sides. So in MathWorld, we have 2 modes of operation. We have the passive mode, where we advert and diffuse the hydrometeors in this case. And we don't activate the microphysics. So we try to build into MPAS ideas. And in the active mode, the MathWorld passive hydrometeors are better like tracers, and in the active mode we nudge the result hydrometeors towards these tracers only at the beginning of the simulation in the first hour or so. So this is an effort to sustain or to provide the appropriate thermodynamical environment to sustain the clouds. So both modes are designed to avoid rapid dissipation of clouds in the short term. Here are more details of the model. And what I want to highlight here is the cloud initialization component. We can use available hydrometeors from the first guess, if available. If not, we can use relative humidity to initialize the hydrometeors. And we can also use Earth observations to refine this first guess. We can impose the cloud mask and the cloud top or base height. We can use satellite retrieval for that, or for the top and the mask, or meter observations we've been using for the cloud base height. And then we have the 2 modes that I already described, the passive and active. And for more detail, how to run the model and all the nameless options you can use and the modes, you can take a look to the readme.mathworld file in the doc subdirectory of Word. And this is a recent publication where we summarize the model and an evaluation. That is what I'm going to focus in the rest of the presentation. I want to show you how the model compares with World Solar. And I will use results from a demonstration where we ran World Solar and MathWorld both in passive and active mode. And we ran it over Conus, 9 kilometers grid spacing, and this is a nowcasting application, so we run the model every hour for 6 hours of lead time. And we use GOES16 cloud mask and cloud top height to refine the first guess. And then for the base height, we use meter observations. And the evaluation is against the SURRAT and SOLRAT, 14 high quality observations over US, the black and blue dots here. And also from the US CRN network, that it has better coverage and over Conus. There are over 100 sites. Again, this is from the publication. So I selected a few plots or results from that article. This is how the errors grow as a function of the lead time. So here are all the simulations from World Solar and MathWorld for a year. And in the first row is the mean absolute error, and in the second row is the bias. And the first column is for SURRAT sensors, and this is from the USCNN locations. You can see that in MathWorld, the passive mode, the errors tends to grow linearly with the lead time, like we found in MathCast. And there is an improvement with respect to World Solar at the beginning of the simulation. This is 15 minutes into the forecast, so it's roughly a 15% improvement. And this is a consequence of the initialization. And then if we focus on the active mode, we see that at the beginning in the nudging phase, which is 1 hour, is similar to the passive mode. But then after we release, we stop doing the nudging, we see a rapid degradation. And this is because we are losing clouds, as we see here from the bias is increasing. So we can probably do better here. But we look towards the end of the 6 hours lead time, we see that after the model has stabilized, we still see a differential with respect to runs with World Solar. And this is statistically significant. This is in the bias. You see that the World Solar has a positive bias, and here in the World Solar runs we didn't activate TANGs, shallow cumulus parametrization, that we usually activate to take into account the subgrid scale clouds. But here we wanted to focus in the result hydrometeors. So the model has a positive bias, and with MathWorf we improve at the beginning, and then as I mentioned, we have some loss of clouds after in the active mode after the nudging phase. In the passive phase, the bias is reduced, but this is because of the cloud out spreading, but the error grows. We are only helping with the systematic part. And both USCRN and SURRAT show similar results, which is reconforting. This is the other result that I want to show, to generalize the previous result as a function. These are the mean absolute error and the mean bias errors as a function of the time of the year. And you can see MathWorf in green and red. The errors are consistently lower than World Solar in blue. And this is what we saw before, but it happens through the year. And I also put the errors of climatology in black and clear sky predictions, and MathWorf is skillful with respect to this reference forecast. Similar comment with the bias as we saw before. World Solar has a positive bias all year around, and with MathWorf we tend to reduce it helps with this bias reduction. Again, this is for 50 minutes into the forecast. So more details on the publication if somebody's interested. But to summarize the presentation, we have added to World Solar the World Solar EPS model, that it has been designed to provide a probabilistic forecast tailored for solar energy application. We have also added the MathWorf model that is designed for short-term irradiance predictions. It has a cloud initialization module and 2 modes of operation, the active and the passive. And both of them are part of the official Word release. I have one last slide with some resources, the model websites, and any technical question you can send it to the World Solar Forum, and with any other thing you can send me an email with my email. Thank you. I'll take questions now.
Thank you very much, Pedro. Doesn't look like we have any questions in the chat. We'll give another couple seconds in case anybody is typing, but okay, yeah, well, in the interest of time, we'll move on. Thank you, Pedro. Next up, we have Joe Klemp discussing modifying the height-based vertical coordinate system in MPAS. So, Pedro, if you could, there you unshare your screen. And Joe, there we go. Thank you very much, Joe. Go right ahead.
Working. Can you hear me okay?
Can see it and hear you.
Okay. Yeah, over the last couple of years, Bill Skamrock and I have been working to extend the capabilities of MPAS, of the MPAS dynamical core, to make it more suitable for deep atmosphere applications that may extend well into the thermosphere. This raises a number of interesting issues because of the extreme conditions that exist going all the way up to the thermosphere. This slide illustrates some of them. For example, the thermosphere, which goes from around 100 kilometers up above 500 kilometers even. Often the temperatures are typically between 1,000 and 2,000 degrees. When we look at some of the other fields, between the surface and around 500 kilometers, pressure and density drop off by 10 to 12 orders of magnitude. So it's really huge. Another interesting feature is that molecular viscosity, which is, of course, negligible in the lower atmosphere, because of the large decrease in density, the kinematic viscosity increases to very large values and becomes a significant influence in the thermosphere. just to put this in perspective, the International Space Station, the altitude of its orbit is typically around 400 kilometers. So this can get way up there. In looking to extend MPAS to deeper atmosphere applications, the first order of business is to remove the shallow atmosphere approximation. And to do this, we have needed to take into account the actual geocentric distance from the center of the Earth instead of just assuming that using the radius of the Earth in the governing equations and in the mesh configuration. Because now we have grid volumes are increasing in size as you move to higher and higher altitudes. Also, now we have to account for the gravity decreasing with height as well. And also we need to include the full Coriolis terms, which includes vertical velocity components. With these additions, the model is appropriate for applications that go up to maybe 150 or 200 kilometers. As we go higher into the thermosphere, now including variable atmospheric composition and its coupling to the dynamics becomes important. As I mentioned now, including kinematic viscosity and thermal diffusivities terms are needed. There's also a variety of physics and chemistry, which is specific to the upper atmosphere, which will become important. The part I'm going to be emphasizing and talking about today is also the need to modify the vertical coordinate to permit a constant pressure upper boundary. To give you some motivation for this, this slide shows a vertical cross-section along the equator taken from the WACM X model. And what it shows in this left panel, you can see the large variation in temperature throughout the thermosphere between the daytime and the nighttime part of the globe. And this indicates very strong diurnal effects of the absorption of energy from the sun. And in this example, the temperature difference between the warm side and the cold side is about 300 degrees Kelvin. The top of this plot is showing the location of a constant pressure surface that is used in the WACM model. And so you can see from this that the atmosphere is expanding vertically, significantly, expanding and contracting as they go through the diurnal heating cycle in the thermosphere. There also can be significant horizontal velocities of well over 100 meters a second. Now, MPAS uses a height-based coordinate. Of course, this is a terrain following hybrid coordinate down at lower levels so the coordinates follow the terrain near the surface. But with the hybrid coordinate formulation, the influence of terrain is totally removed by the time you get very far into the stratosphere. So in the upper atmosphere, you just have constant height coordinates. In order to modify this to allow the upper boundary to follow a constant pressure surface, what we do is essentially implement an upside down terrain following coordinate given by the expression up at the top of the slide here, where now we are gradually adapting the coordinate surfaces so that at the top they follow a surface at height shown here h, that corresponds to a constant pressure surface. Now, the additional complication here is that whereas the terrain is fixed in time and space, the pressure surfaces are varying in both time and space. So the trick now is to have this varying upper surface follow a constant pressure surface. We do that by utilizing the hydrostatic equation applied along the upper surface, so that as we're integrating essentially at every time step, if the pressure is trying to become a little bit more than or less than the desired constant pressure, the height of the surface is adjusted accordingly to keep it following the constant height surface. When we do this, this upper boundary is still a material surface, and but now the vertical velocity, of course, now is varies along that surface. To test this, we constructed an idealized case for diurnal heating that's sort of qualitatively similar to what we saw on that Wacom cross section, where we have a variation of temperature from a warm side to a cold side of the Earth. We're doing this in just a 2D slab prototype version of the model. And what we do then is to impose a heating function in the thermodynamic equation that will propagate this diurnal temperature variation around the globe, so it has a cycle of 1 day to repeat itself. And so if in this, the linear analytic solution from this will just exactly repeat itself every day. If the simulation that we get from our MPAS prototype is shown across the top here, you can see the temperature is back to something very similar to what it started with. There is some skewing and deviation from what the analytic solution would be, and that's because the horizontal velocity is significant and causes deviations from that analytic solution. If we put in increased dissipation to decrease the horizontal velocity, the temperature correspondingly becomes much closer to the analytic solution. In addition, we can compare the solution to what we would get in a comparable simulation from the WRF model. Now, the WRF model has a pressure-based coordinate system, and so its upper boundary is naturally a constant pressure surface. And so in running the same test case with WRF, we see we get very similar results to what we had in MPAS. Well, we can expect that because we see the atmosphere expanding and contracting vertically so significantly, that if we try to do the same test case with a rigid lid upper boundary, there could be it could be quite problematic. We can illustrate that here with essentially the same initialization, very slightly simplified, so that we could generate an analytic solution for the rigid lid case. So if we do this case with the rigid lid, first of all, by simulating this case with our constant pressure upper boundary formulation, we get a solution that's very much what we would expect of just this constant temperature difference propagating around the periodic domain. However, if now we impose the rigid lid upper boundary, now in the lower part of the model, we get results that are very similar to what we had. But now, because the vertical velocity has to go back to 0 at the rigid lid, we get large artificial perturbations just beneath the upper boundary, which are obviously artificial and problematic. So in summary, I think our conclusions are that our height-based hybrid terrain following coordinate remains well suited even for deep atmosphere domains, although when these applications extend into the thermosphere, in order for us to realistically simulate the flow, we need to modify the formulation so that the upper boundary corresponds to a constant pressure surface and allows vertical expansion and contraction of the atmosphere. And with our idealized diurnal heating test case seems to confirm the viability of this technique for generalizing the height-based coordinate. So I'll stop there and take any questions.
Thank you very much, Joe. We do have one question in the chat now for Alan Rosales. When can we use the MPAS with this hybrid vertical coordinate system?
Good question. As I mentioned, we've implemented this for testing in our prototype model. Our plans are to put it into the full MPAS in the reasonably near future. So hopefully it'll be within the coming year.
Okay, any more questions? Last chance until the end of the session. Okay, we'll go ahead and move on then. Thanks again, Joe. Our next speaker is Jeff Wilson, who's going to be talking about the development and evaluation of a coupled MPAS CMAC modeling system. So take it away, Jeff, whenever you're ready. We can see it. I can't hear you.
Yeah, sorry. Couldn't get, trying to get unmuted here. Can you hear me now?
We can, yes.
All right, fantastic. Let me get back to it here. All right, yeah, thanks for having me. I'm Jeff Williston. I'm with the EPA's Atmospheric and Environmental Systems Modeling Division, and today I'll be talking about the work we've been doing to couple the MPAS atmosphere model with the Community Multi-Scale Air Quality Modeling System, which is the EPA's chemical transport model. So why couple MPAS with CMAC? I was asking this myself, if we want to do global air quality modeling, why don't we just lean in on developing geochem or contributing to another effort like SEMA effort? And setting aside the science processes that are different in CMAC compared to these other model options, CMAC is currently used at the EPA for both research and regulatory applications. And something I hadn't realized before I joined the EPA is that when you're using a model for regulatory applications, there's some upside to having in-house development with developers that can sort of stand trial, so to speak, and answer for their design choices. So we really want CMAC. And then why MPAS? In my experience, MPAS is better for global modeling than WRF. I think that's probably a consensus view. And on top of that, it has seamless refinement to smaller scales. Our branch has done some hemispheric scale modeling with WRF CMAC with a nest over CONUS. But when you do that, you have the domain and boundary conditions, both of the parent and the nest, to deal with, and those have been undesirable in our experience. MPAS is also a natural extension of WRF CMAC. It has similar physics. It has a fairly similar workflow. And lastly, we're very excited about this SEMA effort where with the inclusion of MPAS, that provides a pathway for CMAC to potentially benefit from other Earth system modeling components, like ones that are currently in CESM. So a lot of good reasons to use MPAS. Currently, we have MPAS version 7.1 coupled with the EPA's CMAC version 5.3.3, which is the latest publicly available CMAC. CMAC is called as a module in MPAS with data transfer that's similar to how it's currently done in the WRF CMAC, and I think that's already in the WRF repo, as talked about this morning. Advection is handled only on the MPAS side because CMAC's computational grid does not support unstructured meshes, so advection is purely MPAS, horizontal advection. So we have MPAS atmosphere with the CMAC for all these different chemical processes. For air quality purposes, we've added some US EPA physics modifications to MPAS atmosphere, including the addition of the ACM2 boundary layer model, its partner, the PX land surface model, some tweaking to the Kane-Frisch convective scheme, and then added the FDDA that was described by Bullock et al. 2018, just simple grid nudging, and soil moisture data assimilation for PX. All these changes were tested to make sure that they're suitable, that they produce a suitable result consistent, with the WRF CMAC standard. And those results are described by Gillum et al. 2021, showing that we now can produce meteorology for CMAC that's reasonable and usable. So for our experimental configuration, to test it, we're running a few different experiments. I'm going to talk mostly about our coarse mesh configuration today, where we're initializing with CAMS reanalysis ozone. That's an IFS model product. And we're using a maritime model profile for other chemical species. So initialization will be fairly clean throughout the globe, but not zero. So it has a fairly fast spin up, we find. And then we're running the 120 kilometer mesh for years, and then we can take initial conditions that'll be chemically consistent for higher resolution meshes like the 9225, eventually the 6012, and initialize without having to spin up for as long. We enabled the EPA added physics that I talked about in the previous slide, and including grid nudging. And then we're also nudging the stratospheric ozone from the CAMS reanalysis, because stratospheric chemistry is not CMAC's strong suit. For emissions, we've got the 2016 NEI, we've got HTAP, and for outside of the United States, we've got some online emissions, including biogenic emissions from Megan. We've also got online dust and sea spray aerosols. All right, so on to results. At the EPA, we're especially keen to have a model that can simulate reasonable ozone concentrations at the surface. Here's 1 year of simulation for the 120 kilometer run. On the top, we have observations from the air quality system monitoring network in gray, and then the model is in red. And this is 8-hour max ozone. And then you can see the bias here, and you can see the spatial distribution of the seasonal biases for April, May, June, July, August, and then later in the year. So what we see is a low bias throughout in the springtime that sort of transitions to this bias where it's low in the west and then high in the east. And this is a bias that we've seen in other CMAC runs, annual runs, and so it's a bias that we're familiar with, and it's not bad. We're somewhat satisfied with this bias. Moving away from the surface, we can compare with ozone sondes. Here's a selection of ozone sondes I've chosen that demonstrate sort of what we're seeing more generally with the model. These are the points in the stars here. And what we're seeing is a mid-troposphere low bias, especially in remote environments. I included the South Pole here. You can see it's pretty low. The blue is model, red is observations. And then even if the model is fairly accurate, like you can look at Boulder here near the surface, once you get up into the mid-troposphere, you see that low bias come up. And we've seen this through a lot of ozone sondes. And even, we're thinking, well, maybe it could just be because the spatial distribution of ozone at 500 millibars is fairly heterogeneous. Maybe there's just a slight shift in where the ozone concentrations are. So we can look at an aggregate now of zonally averaged ozone to sort of rule that out. And here we see on the top is MPAS CMAC, and on the bottom is that CAMS reanalysis product I've been mentioning. On the left is 2014, on the right is 2016. So this is zonally averaged ozone, and you can see the stratospheres in black here. And what we see is a low bias relative to CAMS, especially in the tropics. And we've run for a couple extra years, and we don't see much change in the tropics or throughout in the bias, much improvement. So we've sort of ruled out, along with looking at carbon monoxide and other species, we've sort of ruled out the possibility that this is just an ozone, or spin up issue for the low ozone bias. So it just seems to be a systematic bias in our model. All right, let me go back to the surface. This is the July average 0Z or surface ozone concentration, and just comparing with other model products to see how we're at, or where we're at. And we compare it to the GEOS composition forecast system. This is NASA's model. I think it's a 1/4 degree, so it's pretty high resolution. They also struggle with the low ozone bias in the mid-troposphere, and they don't have 2014. So just did a 3-year July average here, just for a rough comparison. But you can see their values are fairly low. And then in the middle, we have MPAS CMAC 2014. Summertime is a little bit higher. And then we have the highest, which is the CAMS product, the ISF ECMWF product, and it has the highest surface ozone. So I would say that MPAS CMAC seems to be in a ballpark with other leading models. You know, I don't know if it's like the correct ballpark, but it's in range with these other models. Also want to touch on resolution. We have a reasonable expectation for ozone that as you increase resolution, you'll get more ozone. Here's July 2016 simulation on the 120 kilometer mesh on top for average 0Z ozone, that's why it looks higher in the west. And below is the 9225 mesh, and it looks nicer, but it doesn't really help our low bias. The higher resolution simulation 8-hour max ozone is in the blue line here. You see it's the lowest, and then next up is the red. That's our 120, and then the observations are up here. So it could be something to do with, but there's some nuance in how we process the emissions for the 92 for the higher resolution mesh versus the 120. So that could be part of the issue, but it's pretty clear that just increasing resolution is not going to be a panacea for fixing this issue. Lastly, I want to talk about another thing that we care about at EPA is surface PM 2.5 concentration. What we see with our MPAS CMAC run is a general overestimate. Again, the model is in red, observations are in gray here, and this is a full year. So we're seeing a general overestimation throughout CONUS. And you can see the bias is positive everywhere and mostly focused on the eastern part of the domain. If you look at the breakdown of what contributes to PM 2.5, the gray is organic carbon, and you can see on the left, this is observations. I have my cursor in the wrong place this whole time. On the gray, on the left is observations, on the right is the model. And you can see that we have a lot of organic carbon, probably partly due to Megan 3.1. So we have some ideas on how we can improve that. And then upcoming CMAC 5.4 will have aerosol deposition changes where it has a more realistic representation of leaves, hairs on leaves where it'll increase deposition is what we've seen. So this bias should come down. So just in summary, where we're at is we've coupled MPAS atmosphere with EPA's CMAC model, and we've been simulating multiple years. We've been simulating different meshes. And in general, what we're seeing is a mid-tropospheric low ozone bias that's similar to what GeoCF is experiencing. Could be convective, could be lightning knocks. We aren't really sure yet. We're working on addressing that. The surface ozone biases, at least over CONUS, seem to vary by region and season in a way that we're somewhat comfortable and familiar with so far. And then PM 2.5 has a high bias that we're pretty sure we're going to be addressing in the very near future. And what this all means is that MPAS CMAC is approaching very quickly a state where it's ready for research use, and we can start moving forward away from testing and more towards research. Part of that future work will be testing higher resolution meshes, including a 6012 mesh, again, for refinement over North America, exploring the effects of direct radiative feedback from aerosols, and then doing more runs in the 9225, and then updating to the latest CMAC 5.4, which isn't released yet. It'll be released soon, but it's important to keep those, the couple of components up to date. And on that note, you know, it's not listed here, but other future work would be including those EPA modifications to MPAS into the MPAS repo is on our to-do list. So just a quick summary, and thank you.
Thank you very much, Jeff. We have a question for you from Mary Barth. Did you evaluate the PBL height from MPAS CMAC with observations? Any chance it's affecting surface concentrations?
Yeah, we have a few problems with PBL. We've looked at that a few times. You might go to Rob Gillam's paper, that 2021 paper. It's in the references of the slide deck for, I think he looks more at PBL height and has some figures in there, but we do have issues with PBL height. Another issue we need, or that we think will help with this is is upgrading to Morrison microphysics, which I don't think is an option yet in MPAS. but for Warp CMAC, I think that's better. It gives us better results. And yeah, I'm not sure where else for the ozone concentration we can look. So.
Okay,
soil
thank
moisture
you.
Data assimilation methodology.
Yeah, go ahead.
Sean Pline could talk more about that. I haven't done a lot of work specifically on that, but it's just the same as the PX scheme has been doing it for years, as far as I'm aware. And it's a indirect soil moisture data assimilation. And then Jeff, do you see improvement using global MPAS versus regional WRF, for example? No, I mean, right now, regional is sort of the standard. So we're just trying to get to that point. I don't know if we're quite to where we can say that we're seeing improvements, especially because for regional WRF, it's much more affordable computationally. So we can run a high resolution. So it's hard to compete at the resolutions we've currently been running at. Service bias, yeah. So thanks, Jimmy.
Okay, hold for a couple seconds here, but looks like the questions have died down. So thank you again, Jeff.
Thank you.
Next up, we have Laura Fowler talking about bringing in realistic aerosol emissions and initializations to improve CCN and ice nuclei representation in MPAS. So take it away whenever you're ready, Laura.
I'm not sure if you see my full screen now or not.
We see not full screen yet.
There we go.
There we go.
Okay, thank you. So I'm going to present some results in which we are trying to bring realistic aerosol emissions and initializations of to improve CCN and IAN representations in MPAS forecast using the aerosol-aware Thomson cloud microphysics parameterization. So a few words about the parameterizations itself. The aerosol-aware options includes the activations of cloud condensations nuclei and ice nuclei based on two groups of aerosols. One aerosol category is what Thomson describes as water-friendly hygroscopic aerosols, which include organic carbon, sulfates, sea salts, and some small dust. And the second category referred as the ice-friendly non-hygroscopic aerosols that are used for cloud ice activations, and which basically includes non-hygroscopic dust of mass larger than 0.5 micron. So in its original implementations, the global distributions that are interpolated to MPAS are from monthly mean waterfront, are from a monthly mean go-kart simulations. So this panel here shows simply shows a vertically integrated amount of water-friendly aerosols initialized on June 6, 2012. And we see a high amount of water-friendly aerosols over the rain and rainforest in Africa, South America, as well as a lot of water-friendly aerosols along East Asia, Europe, and the Eastern United States. So for the water-friendly aerosols, Thomson uses in its default parameterizations a very highly parameterized surface emissions, which is shown here. That surface emissions depend on the initial amount of water-friendly aerosols in the layers adjacent to the surface, and it's a constant throughout the model forecast. For the ice-friendly aerosols, we actually need to link the scheme to a specific dust model available, for instance, on the chemistry side. So the goal of this talk is to implement physically based aerosol cloud interactions that would include surface emissions of anthropogenic aerosols. Here we use the monthly mean CAMS inventory. We want also to provide realistic initializations of aerosols using CAM-CAM outputs, and use parameterized emissions of natural aerosols like sea salt and dust using the go-kart bulk aerosol models. That way we can specifically start to add links between physics and chemistry. So in its current status, the physics schemes that we're using are the Thomson aerial options that allows nucleations of water-friendly aerosols to cloud water droplets, as well as nucleation of ice-friendly aerosol to cloud ice crystals. We also use the scale-aware Grell-Freitas convection scheme, to which we added the convective transport of aerosols and passive tracers, and it includes weight scavenging in updraft and evaporations in downdrafts. And finally, we added the EDMF PBL scheme, which allows the transport of aerosols and passive tracers and other chemistry species in a PBL and a free atmosphere. So here is an example of early work that we did using this set of parameterizations. It simply shows a transect of water-friendly aerosol across the mature stage of a mesoscale convective system that was observed during DC3 in 2012. And those plots really show the difference between the vertical distributions of the water-friendly aerosols when we use an implicit convective transport that is needed when MPAS is run with a quasi-uniform 15-kilometer mesh, versus the explicit convective transport of water-friendly aerosols when we use a 15 down to 3 variable resolution mesh centered over conus. Note that in those two plots, we didn't use the surface emissions because the actual parameterizations of surface emission that I described above produced a lot of aerosols that was producing quite a realistic forecast. So we decided to add a simple go-kart-based schemes to update anthropogenic sea salt and dust aerosols using those realistic surface emissions and have that connected to our physics parameterizations. And to do this, to initialize MPAS, well, first for the surface emission, we use the CAMS monthly mean inventory to update the anthropogenic organic carbon and sulfate. We use the go-kart base schemes to update sea salt, dust aerosols using the simpler go-kart emission schemes. And we use the CAM-MAM4 outputs to initialize anthropogenic and natural dust aerosols, natural sea salt and dust aerosols. MAM4 standing for the model aerosol module version 4. And that was, again, put on the top of the actual simple chemistry model. So the monthly mean emissions of organic carbon and SO2 were taken from the Copernicus Atmosphere Monitoring Service CAMS, and they have been interpolated to the MPAS meshes using a Python-based ESMF regulating script developed by Dusung Zhou. So it's an external tool that actually kind of allows us to interpolate latitude, longitude, grid emission in a quite simple manner and actually a pretty fast manner as well. So those interpolated monthly mean surface emissions are then read as an input stream directly to MPAS and interpolated to the initial start time. They can also be updated for longer forecast if we needed to. So those three maps here shows simply the surface emission of black carbon, organic carbon, and SO2, again showing increased emission over India, Southeast Asia, Eastern Asia, Europe, the Eastern United States, emission of organic carbon over Africa, South America, and here in the case of SO2, the additional emission over ship tracks. So the second step in our initializations of the aerosols of the aerosol MAM4 model, taken from the MAM4 model to the Thomson aerosols, it's actually a two-step process. So first we need to take the MAM4 aerosols and map them to the go-kart aerosol models. And we do that so that we can first retain the compositions of water-friendly and ice-friendly aerosol, which was first proposed by Thomson and Hadheimer, in order to not right away implement too much complexity in our schemes. And we can also that way retain the simple parameterizations of the natural aerosol, sea salt, and dust that is provided by the bulk Go-Kart aerosol model instead of implementing MEM4 directly into MPAS. So the MEM4 aerosols are organized by different, through 4 different modes: a primary carbon mode, an accumulation mode, an Aiken mode, and a coarse mode, whereas the Go-Kart aerosols are organized as hydrophobic organic carbon, hydrophilic organic carbon, sulfate, then 4 beans of sea salt, and 5 beans of dust. So the Emmons, that mapping from MEM4 to Go-Kart that was first proposed by Emmons et al., for instance, take all the aerosol species and number concentrations available from the accumulation mode and split those into hydrophilic organic carbon, sulfate, and small sea salt. And then it takes the coarse mode provided by MEM4 and it split that into sea salt of larger mass size, and then the first 3 beans for the Go-Kart dust model. The second step, now that we have mass mixing ratio and number concentrations of aerosols from Go-Kart, is to group them so we can come up with one field of water-friendly hygroscopic aerosols and one single variable of ice-friendly non-hygroscopic aerosols that are input to the Thomson cloud microphysics scheme. So we group the hydrophilic organic carbon, sulfate, and small sea salt to the water-friendly hygroscopic aerosol category, assuming that the number concentrations of those water-friendly aerosols now is similar to that from the MEM4 accumulation mode. We do the same for the ice-friendly non-hygroscopic aerosols, and we group the first 3 beans for dust into that one category, assuming that the number concentrations of ice-friendly aerosol now is similar to that of the MEM4 coarse mode. So this plot shows 4 different panels. The 2 panels on the left-hand side shows the global distributions of water-friendly aerosols in the layer adjacent to the surface on June 6, 2012, which is the initial condition that we use for some of our experiment. Water-friendly aerosol in this panel and ice-friendly aerosol for this bottom panel. And as for the Go-Kart distributions, we see increased water-friendly aerosols over the rainforest and forest of Africa and South America, as well as an increased amount of water-friendly aerosols in the layer next to the surface over India, East Asia, the United States, Europe, and over the Malaysia. For the ice-friendly aerosols, we of course see an increased amount of ice-friendly aerosols over the desert regions, including Australia and South America. Now the plot on the right-hand side now shows the difference in the water-friendly aerosols and the ice-friendly aerosols at the end of a 5-day spin-up relative to the initial conditions. So in this panel here, we see increased amount of water-friendly aerosol due to that emission map that I previously showed. And we also see large decrease of water-friendly aerosols in that layer adjacent to the surface. Those areas of decreased aerosol corresponds also to areas of pretty large amount of total precipitations, which indicates the removal and nucleation of water-friendly aerosol, not only by the implicit convective transport from the GF scheme, but also by the scavenging and conversions to cloud water droplet by the Thomson microphysics scheme itself. For the ice-friendly aerosols, we see an increase in the amount of ice-friendly aerosols over the desert area as well as the decrease of aerosols in some area, for instance, like Australia, corresponding to advection, removal by scavenging by the Thomson scheme, as well as productions of ice nuclei. This next plot here now shows the zonally average vertical distributions of water-friendly aerosols. The zonally average is taken between the equator and 10 degrees south. This is a map at the initial time on June 6, 2012. This is the area of Africa, for instance, that I showed in the previous slide. After a 5-day spin-up, this map also shows the vertical distributions of water-friendly aerosols after a 5-day spin-up. This one is with convective transport, but without the wet scavenging option. Whereas this next plot here shows the same vertical distributions, but when we include the wet scavenging of aerosols by the GF scheme. So we can, relative to the initial conditions, we see the strong impact of the not only of the convective transport, but as well as wet scavenging in the upper troposphere. So in conclusions, we've built and tested the novel initializations of aerosol in MPAS. We mapped the CAM map for aerosol to the Thomson aerosol scheme. We have added realistic surface emissions of anthropogenic and natural aerosols such as dust and sea salt, and initial spin-up runs and forecasts are, as we expect, and quite encouraging. So the future work will include to reduce some of those earlier experiments that we did last year without surface emissions, but now using realistic surface emission and initializations of aerosol, and probably expand our implementations to other variable resolution experiments, for instance, experiments that can take place like during Eclipse or Precip for that matter. Thank you very much.
Thank you, Laura. Great talk. Do we have any questions for Laura? Okay, this is from Alan Rosales. Are the aerosols continuing introducing into the model during the simulation MPAS, or do they only add in the initial conditions?
Well, no, they are added during the simulations for both the anthropogenic and anthropogenic aerosols. I mean, we have a constant surface emissions, as well as using the go-kart based model, we have an update of those aerosols through the emission of dust and sea salt using the go-kart emission schemes.
Okay, I think that is it. Thank you again, Laura. We'll move on to our last talk of the session. This is by So-Young Ha, going to be talking about weakly coupled DA with aerosol cloud interactions in WRFChem WRFDA. You can see, there we go, full screen.
Okay, so can you hear me okay?
And
can you hear me?
Yes, we can hear you. Go right ahead.
Okay, good. Hi, this is So-Young Ha from MCube in Data Simulation Group. Today, I'm going to introduce a new feature I implemented in WRFDA 3D bar system for the weakly coupled data simulation with aqueous chemistry for aerosol cloud interactions through WRFChem model. So this work was, this development task was partially supported by the Korean National Institute of Environmental Research, which is in charge of operational air quality forecasting in South Korea. For the last couple of years, I actually expanded the WRFDA 3D bar system for the Rackham gas and MADE-VBS aerosol chemistry scheme. In data simulation application, a simple go-kart aerosol scheme has long been used, mainly because it's simple, especially for the AOD simulation from the satellite retrievals. but in the more advanced aerosol scheme, like a mud aerosol here, which is a modal scheme. So it defines the aerosol particle size distribution as a superposition of the three low normal modes as shown on the right. So aqueous mode is the smallest particle, and then accumulation, and then coarse mode. So in the weakly coupled DA, we can assimilate the meteorological and chemical observations at the same time, but independently, which means that the meteorological variables like a UVT cannot see the chemical observations in the analysis and vice versa. But when it comes to the forecast, these variables are fully coupled through the WRF model. So as Ek et al. In 2018 reported, the major aerosol pollution transport events over East Asia were often associated with extensive cloud cover, but these cloud cases are hard to be observed, especially in the remote sensing data because of the cloud contamination. They are mostly reported as missing or available in a very poor quality. So the lack of the observations, makes us rely on the model even more to make it more critical to reduce the model error with advanced physics like aqueous chemistry in this case. So the aqueous chemistry in the WRF model, the aqueous chemistry is required to simulate the aerosol cloud interactions. And here I adapted the page from the WRF tutorial, which was so helpful, I should say. And I tried to understand all this complicated process behind all the different options. And to interact with clouds, aerosols should exist in cloud water or in the aqueous phase. So we call it aqueous chemistry. So we have to activate that, which is coupled to Lean or Morrison double moment microphysics scheme in the WRF model. So like without chemistry, in the simple case, the chemistry option is 0 in the WRF weather simulations. Then the cloud droplet number, concentrations, and size distribution are all prescribed. But with the chemistry compiled, we can specify the chemistry option. And in this particular case, I used 108 for the Rakamade VBS chemistry, and then I expanded to 109 with the aqueous chemistry. And in that case, the number, droplet number concentration and the size distribution, those are all treated prognostically. And we can simulate the wet removal processes as well, where the cloud-borne aerosols are collected by both grid scale cloud microphysics and the convective precipitation. But without aqueous chemistry on, the aerosols cannot directly affect the formation and growth of clouds and cannot be displaced through convective transport or removed by wet scavenging in the WRF model currently. So in the assimilation, in 3D bar algorithm, we are basically minimizing the cost function J as a function of V, the control variables, by reducing the innovation D here, which is the discrepancy between the observation Y and the model correspondent H of X here, using the background error covariance here, the square root of B, because we are trying to avoid try to avoid the computation of the inverse matrix, B to the -1. So we instead go through the series of the matrix transformation as shown at the end of this line to compute the square root of B, which I'm going to show in the next slide, which is going to be used as a relative weight to each aerosol species. So for the new development, for a particular chemistry option, which is 108 or 109 in this case, we have to expand the control variables to accommodate all the aerosol variables, because each and every chemistry option defines its own, a unique set of the chemical species. So we have to develop the DA system specific to the chemistry option. So as well as the control variable, we have to expand the background error covariance and then observation operator for a special observation type. So in this case, we are assimilating the metadata as well as the aerosol observations. So they are all included in the control variables and the other components too. For the PM 2.5 assimilation, for example, the observation operator H of X is composed of all the as a like a total sum of all the aerosol species defined in this particular chemistry option. For the aqueous mode I and the accumulation mode J for 2.5. And with the aqueous chemistry, each aerosol species in each size mode, they exist in the aqueous phase as well. So it's basically double the size of the variables, number of variables. So we just add up all of them to compute the PM 2.5 here. This is just to follow the way the model estimates the PM 2.5. And for the PM10, we just add up all the coarse mode aerosols to PM 2.5. So in the WRFDA system, the interstitial and the cloud-borne aerosol particles are treated explicitly. And for each aerosol species, cloud-borne particles in 3 different modes are added in control variables, observation operator, its tangent linear and adjoint versions, and background error covariance as well. So in 3D-VAR algorithm, the background error covariance is quite critical because it determines how to spread out the observed information both horizontally and vertically, and it gives relative weight to aerosol species. Because when we assimilate the surface PM concentration as a total sum of all the aerosol species, we compute the analysis increments in PM concentration. And then we have to decide how to project them, distribute the increments in PM concentration back into each aerosol species. That is determined by the background error covariance. So that's why it's critical. And WRFDA system supports various ways of computing the background error covariance. And we chose CD option 7 here, where all the control variables are treated as full fields, and there's no cross correlations between chemical species and the cross correlations between chemical and the meteorological variables. So the Jimy software is the one that is computing the background error covariance. So that has had to be expanded for the new chemistry option to accommodate all the aerosols in the aqueous phase. The total number of variables was increased from 45 to 80, including all 6 meteorological variables as well. The aqueous chemistry mostly affects the surface formation, and the simple aqueous chemistry implemented in the WRFChem model is just working for the warm rain process only. So it affects like a mid to low troposphere basically. And so I show the background error covariance here as a square root of B, as I showed in the previous slide. In the interstitial phase, the surface in the interstitial phase on the left, and then all the variables in the aqueous phase on the right. So this background error standard deviation is basically telling you how much weight we are going to give to this particular aerosol species. So with and without aqueous chemistry, we can see that the aqueous chemistry is trying to reduce the surface in the interstitial phase up to level 22 or 3, although but like on the other hand, in the aqueous phase, the surface was mostly increased, in the low troposphere, in the accumulation and the aqueous mode. So the cycling experiments, the one-way nesting in 27-kilometer resolution over the East Asian region, and then 9-kilometer one-way nesting to the Korean Peninsula at 9-kilometer resolution with the 31 vertical levels up to 50 hectopascal. And I assimilated a surface PM10 and 2.5 observations, as well as the NCAR prep for all the conventional meteorological observations every 6 hours for a month of March 2019, starting from February 21st. Using the chemical option 108, and then I used 109 after expanding the WRFDA system. to compare those two options using all these physics. And I want to point out here that I use the Morrison double moment scheme with all the aerosol, both direct and indirect effects. And in this particular case, we had some high pollution case in the early March, but then so at the end of the period, the cycling period, starting from 20th of March, we had some high cloud extended with a light rainfall event. So that's where we are gonna look at the impact of the aqueous chemistry. So on 20th of March 2019. So there's a high cloud cover, over the entire Korean Peninsula and the surrounding areas, with some the pollution event. And so I conducted 4 experiments with and without data simulation using the chemical option 108 or 109. And on the right, this is the time series of the 3-day 24-hour forecast from the 00Z analysis of each day. So Korea is 9 hours ahead of UTC time. And on the right axis, the mean sea level pressure on the top level, and then the hourly rainfall at the bottom panel. So if we look at the synaptic pattern here, synaptic case here, the mean sea level pressure tells us that the surface low pressure center is approaching the Korean Peninsula at the second day, the 20th of March. And then the surface PM 2.5 and the PM10 concentration shown by the black triangle is almost, linearly decreasing at the second day. And then, associated with the slight, like a light rainfall event overnight. So the 12Z corresponds to 9 p.m. in the local time. So during the nighttime, there's some light rainfall event. So with the aqueous chemistry, orange and red marks, regardless of data simulation, they are following the observations pretty well. But without aqueous chemistry, you can see the blue and green marks, they rather increase the PM concentrations, right? Even after the rainfall event. So I just, zoom in the second day forecast, 24-hour forecast at the time series over as a vertical distribution up to level 20 out of 30. For each experiment from top to the bottom. So the bottom 2 experiments are, use the aqueous chemistry, and not the top 2 didn't use the aqueous chemistry. So the PM10 concentration is colored with the color bar down here. And the right axis in the y-axis on the right is showing the liquid water path with the black dashed line here. So we can see that, with the aqueous chemistry, the Q rain mixing ratio was enhanced, overnight, possibly related to the rainfall event, right? And then, probably the aerosol species, all the atmospheric aerosols in the atmosphere were removed by this slight rainfall. But without aqueous chemistry, the model was overestimating the PM concentration significantly, and that affected the LWP as well. Which was quite different between with and without aqueous chemistry. So there was Seoul, the average over Seoul sites, but not just confined to the Seoul area, but looks like that overestimation without aqueous chemistry was widely, observed in the 24-hour forecast without aqueous chemistry, as shown in the top panel. Compared to the observation, the aqueous chemistry seems to simulate the removal of the aerosols pretty well. Okay, so as a cycling mean, we can see that the data simulation was trying to increase the PM concentration more towards the surface, because we estimated surface PM data. But, like in this particular case with the rainfall event, at the bottom panels, both analysis and background forecast, as shown in like a red and black lines, they reduce the PM concentrations significantly. But without aqueous chemistry, in the orange line, the analysis was trying to reduce the PM concentration, but that was not enough. So that means that, using advanced physics made the assimilation more effective. As a summary, so the WRFDA version 4.4 was expanded for the recommended BBS aqueous chemistry option 109 to assimilate surface PM 2.5 and PM 10. And I didn't show the results of the assimilation of 4 gas species, but they are also, they can be assimilated independently or at the same time, as well as PM concentrations. And these features, actually, I have to mention that the aqueous chemistry for the recommended BBS option had a significant, the major bugs in the model. So they had to be fixed first. So those are going to be all released in the next major release. That's a plan. And the 3D VAR system, the model error is not explicitly accounted for, but introducing aerosols in the aqueous phase in WRFDA seems to be beneficial in simulating wet removal of aerosols in cloudy conditions. And in the strong constraint 3D VAR, reducing model errors through advanced physics mechanisms can make data assimilation more effective. And even though I didn't have time to show, the aerosols interacting with clouds and radiation affected local weather conditions such as PBL height and 2-meter temperature and humidity. And with aqueous chemistry, the surface aerosols in cloud water experience large increases associated with the low-level clouds over the Korean Peninsula, followed by the rainfall event. But this new capability has many limitations, such as simple aqueous chemistry implemented in the model that may not be working for the mixed phase cloud, convective clouds with all the complicated aqueous phase reactions. And the analysis, the aerosol number concentrations are not included in the analysis, so they are not changing, through the data assimilation. So it was hard to actually examine the impact on the cloud size. With that, I'll be happy to take questions.
Thank you very much, So Young. Doesn't look like we have any questions in the chat now. However, we are kind of in the general Q&A session as well. So if you do have any questions for either So Young or any of our other speakers today, speak now or we will be ending soon. Well, it does not look like we have any questions. Wei, I guess I'll turn it over to you.
Yeah, if they're, like, just hold on for a second or two. But yeah. If you have any questions for any of the speakers today, this is a time to ask more questions. But I guess. Yes, I can answer this question. Will the slide be available after the workshop? Yes, the slides in PDF format will be posted on the workshop page. If you have the workshop page now, the link and under the program, there will be another link added for the presentation. Yeah, that remind me, for those of you who have not sent your presentation to us today or later in the week, please do so whenever you have them ready. Yeah. Okay. Well, thanks, Jordan for chairing today's session. And yeah, it looks like we don't have any more questions. Thanks all the speakers. I hope that everybody enjoyed the talks today and learned something from the speakers. There was something. Oh, there's a question. Maybe someone, okay, I'll read it out and see if anybody, this is look like an EPA question. For a new user who wants to learn WRF and the CMAC, is there any place where video tutorials are available? Anyone from EPA willing to comment? I know there is a web page. You can search for CMAC web page, and there are instructions on how you can do it. But I don't know if there's tutorials. Okay. Yes. Someone answered.
Jeff Wilson,
learn
I don't think
CMAC.
we have video tutorials.
Okay. Good. Good. I don't know if Jake is still on. There's a question for Jake Liu. Jake, are you still there? Ming-Chu, I will forward your question to Jake. And see if he has an answer for you, in the next couple of days. Okay. And okay, there's another question. Oh, will there be an MPAS simulation practical demonstration during this workshop? I guess the answer is no. This is a workshop, not well, I guess we call it workshop. It may be a little bit confusing to some people, but it's more like a conference that we share our research and the use of the model rather than learning how to use a particular component model. But there will be MPAS tutorials down the road somewhere if you watch our announcement. Yeah, there will be, but not at this tutorial, I'm sorry. Yeah. Anything else? Yes. Okay. Nothing from YouTube side. And well, shall we conclude today's meeting, and thank you.